let me just repeat the welcome to everybody this morning here in the room and across the globe. It's my great pleasure to chair this morning's session, and if you look at the program, you'll see that physicists believe in symmetry. We've got a nice symmetry of two people on the podium from Birmingham and two from Berlin. And it's my great pleasure to introduce Professor Mark Dennis from the University of Birmingham, which is also my institution, who will be talking about the classical light and its properties to us this morning. I've been told, and I'll just address that to the speakers, that we have to be very strict on timing to keep to our schedule. So the format is 30 minutes presentations, then 15 minutes for question and answers, for which I'll join the presenters on the podium. And there'll be roving microphones for anybody who wants to ask questions from within the room. So if you indicate your intention to ask a question, if you could just raise your hand and wait for the microphone to reach you so that people who are following us through the stream can actually hear the questions as well as the answers. So, Mark, we look forward to your presentation. Thank you. Yes, yes.
Great, thank you. So, as I understand it, what I'm going to be trying to talk about to you today is introducing you to the topic of light, in particular seen through the lens of the history, particularly focusing in my talk on what we call classical light. Now, different people, I guess, depending upon your background, you might have a different interpretation of what classical is. If you're a research physicist, probably classical is anything before 1900, and if you're an ancient historian, classical is anything before 100 BC or something. So what I'm going to do is I'm going to try and focus in a particular period that I think is very interesting, that's in the 1600s, where we have, which is what we would think of as the dawn of modern physics, and think about how the science of light arose in parallel with other sorts of sciences, but also picking up where some of those ideas that were being discussed 300 and so years ago show up a little bit in modern physics. So, apologies to Keats, I'm unweaving the rainbow in the sense of trying to make sense of all of the various different of historical facts as a physicist. So when we say, how should we think of optics, as in many areas of physics, we say, well, why don't we start with Isaac Newton? And when we think of Newton, we think of something like this. This is him in 1687, when his famous Principles of Natural Philosophy was published, which, from our physics point of view, is the laws of mechanics. That's Newton's three laws. It's the laws of astronomy and planets and so forth. It's mathematically, he derives everything mathematically from his three laws with a logical structure following the ancient Greek mathematicians. But when we talk about optics, we're actually thinking of this Newton a few decades later. So the optics, well, this is describing his experiments over the course of his life, but was published in 1704. So sometime after his mechanics. And it's really, if you look at it, although he talks about axioms and proofs, it's really a collection of empirical phenomena. And so it's highly synthetic. It's based on, of course, when we talk about optics, we're talking about stuff we see. And there's not necessarily any logical structure behind the various different sorts of phenomena that we see with our eyes. So when we think about optics, we have to be careful, what is it that we mean? So when we think of optics, we can't separate it from the physiology of human vision, because it's what we see. So in particular, for example, what we know, of course, that we're talking about the full electromagnetic spectrum that has length scales from fractions of the size of an atom all the way to giant, kilometers and longer. And there's this tiny little band which we call optics, because our eyes happen to be particularly sensitive in that frequency range, because it happens that that's the maximum emission from the sun. So these are all, from a sort of physics point of view, coincidences, but yet we still say optics is the behavior of electromagnetism in that range. When we look about the history of optics, though, because seeing is such a fundamental sense for us, of course we want to make images all the time, and images and our imaging systems, our imaging technology, are absolutely central to the science of optics. So we can't separate the abstract science, like we might try with mechanics, from optics technology. So thinking about imaging, we're thinking about lenses, telescopes, microscopes, and so on. So lenses, just to put it into some context, there's evidence. Here's a medieval manuscript, and you can see these monks singing away, and this fellow's got some glasses on. So lenses go back to the 1200s. Telescopes and microscopes, evidence is they were both developed around 1605 in the Netherlands as sort of technological things that were immediately picked up in science. So Galileo, as soon as he got a telescope, he looks up, and this is his sketch of the moon. And Kepler, shortly afterwards, with a refinement on Galileo's telescope design. And 50 years afterwards, Robert Hooke, whose building is just across the way, with his development of looking at various things in microscopes, and his is his famous image of a flea. So alongside the development in the science, and I'll focus on the science, we've got the technology always slightly behind. And because these are so important for astronomy or understanding biology, we often think of optical science taking a supporting role in other sciences. So here I've got astronomy and biomedical. And of course, that's still the case today. So I was thinking, trying to think of some themes of classical optics, and obviously the rainbow is going to be coming up at some point. So I've tried to think that these are 5 themes that I picked out. This is just me thinking of particular themes that come up in, let's say, starting in the early 1600s. Newton discusses all of them at some level, and they all play a role in modern optics as well. So thinking about rays and geometrical optics, mechanical effects of light, waves and physical optics, color and polarization. And this is a bit light-hearted, really. I was trying to think of the various sorts of, the people that I'm highlighting today. So thinking about, we mentioned Kepler and Galileo, Descartes, 1630s, and then, remarkably, in a window of less than 20 years, beginning with Fermat in 1662 and finishing with Huygens in 1678, all of these observations or theories that are fundamental to modern optics, that are before Newton. This was the same period that Newton was working on his mechanics, and he did optics experiments as well, but his book was a few decades afterwards. And then major further developments, Thomas Young in the early 1800s, and then following all the way to Maxwell in the 1860s with his electromagnetic theory of light. And I'm not going to, but I will focus on the sort of these developments and the sort of color-coded to the themes that I picked before. So I'm starting then with rays and geometrical optics, which is where everybody starts, and I can see Tom McLeish in the front row, and he will no doubt want to point out the very detailed arguments of how ray physics started with the Greeks and passed through Arabic science. I instead want to just think of something a lot less sophisticated, and again, I'm thinking from a physics point of view, from the history point of view. So I borrowed my daughter's book, Optical Physics for Babies, which says that light travels in a straight line until it hits something. So that's a good start for what we call about ray theory. And of course, the fact that light travels in a straight line underpins our whole idea of light, what we see, but how we picture it in our minds through geometry. So in fact, the idea of light rays goes back to antiquity, and the name that's often associated with that is Euclid, the same as the person who wrote the book on geometry. But importantly, Al-Haytham in, when was it, about 1100, made the important observation that the arrow points away from the light source and into our eye, because before that, people thought that the light rays came out of our eyes and to the things that we saw. And there was sort of a lot of confusion about that. But as I say, I will treating this, as far as this course talk goes, as ancient history. So I'm sort of starting with, well, 1604, Kepler's book. So Kepler, obviously, very famous astronomer, 3 laws of planetary motion, and he wrote a book, The Optical Part of Astronomy, which is different from the mechanical part, just like Newton talks about. And his optical part of astronomy, he talks, for example, about light going in straight lines, the law of specular reflection that's also ascribed to Euclid, that is to say, angle of incidence equals angle of reflection. He talks about refraction from the atmosphere, but he didn't write down the famous Snell's law that relates the sine of the angle with the normal to the refractive index of the material. That was 1621, so I guess, Joe, if you're looking for historical link for this meeting, it's the 400th anniversary of Snell's law of discovery. And in Leiden, where Snell lived, they've recently celebrated the scientific history of Leiden by drawing famous equations and diagrams on the sides of buildings. But we don't really get rays by themselves. What we have is a light beam is a family of rays, or sometimes called a bundle of rays. And here, through a lens which has been carefully designed to control the refraction, the angle at each of these, where each of these rays comes in, we get that all of these parallel lines all converge to focus. And that's the basic sort of fact of image making. And of course, it requires a lot of engineering to design and deliver a lens of the quality to get all of the rays to come together at a single point. But that is the basic idea behind spectacles, telescopes, and microscopes. Interestingly, that doesn't always have to happen, of course. If you've got a curve that doesn't have this special design, the light rays all come together, not at a single point focus, but typically in 2 dimensions on a line, a bright line, which meets in this case at a point called a caustic. And the first investigation of caustics that we know of is actually Leonardo da Vinci about 100 years earlier. And I'm sure everybody's seen this so-called coffee cup caustic coming from the parallel lines coming in and reflecting on the surface of the coffee. And that's a mathematical curve called a nephroid curve. It also happens for random, if you have a random surface, like the surface of water, you get this random focusing that we all are familiar with on the bottom of a swimming pool. But interestingly, the mathematics behind these caustics was only understood fully in the 1970s as an application of the area known as catastrophe theory. So, why should rays behave the way they do? And that's obviously what we try to do in science, is try to say, if we have a lot of empirical observations, why do they behave the way they do? And a remarkable sort of, as I say, theory, it's a proposal, it didn't necessarily have an explanation for these behavior of the ray of light, came from Fermat, the same person who had a last theorem. This was at a different period of his life, where, I'm paraphrasing, light rays, often we say to students, choose the path which makes the time of flight between the endpoints stationary. So if the light ray starts here and finishes here, a straight line is going to be, assuming it goes equally fast, a straight line is going to minimize the time. It's minimal time, not minimal distance, and Snell's law, where you've got the refractive index changing the speed of the wave, it wouldn't be true if it was minimum distance. So it's mysterious, but it explains the observations. Without Snell's law, without Snell's law, it could have been stationary distance. What this does is it requires light to travel at a finite speed. It's not propagating instantaneously. And actually, first serious measurement of the speed of light was Römer a few years afterwards. And that got refined over the following centuries. But from a sort of more philosophical question, if we're going to say rays have the ability to choose, how does a ray know where it's going to end up in order to choose that minimal path? So mathematically, you can set it up as a boundary value problem, but that doesn't necessarily mean that light knows how to work. And it's actually not even that practical. Hamilton, who you might be familiar with as both in Hamiltonian optics and Hamiltonian mechanics, developed his theory of Hamiltonian mechanics precisely because he was very frustrated in doing experiments shining light into crystals. He didn't know where the path was because he didn't know where to look for the light coming out because he didn't know where it came out. So he formulated effectively Fermat's principle in a different way that's based on initial conditions rather than boundary conditions. And so this leads to a sort of fundamental duality in the idea of what we have, rays and underlying it, waves. What is a ray? So in this Fermat principle, and supported by Newton, he'd say it's the path of a light corpuscle. So of course we have this question that goes on for centuries: is light a particle, is light a wave? And this principle was used as an evidence to argue that it's a particle. If it's a wave, we still have to explain somehow what it is. In our modern theory, we can derive Fermat's principle purely from the wave theory, because what we can interpret is rays are a particularly coherent path in the superposition of waves. Technically, they're saddle points in a diffraction integral, if you know what that means. Otherwise, don't worry or ask Tom in the break. But this is at the heart of the semi-classical analogy between classical and quantum mechanics as well, for example, as picked up by Richard Feynman in his book QED, and used as the fundamental insight into the interaction, quantum interaction of light and matter. Okay, so that's rays. Now what about mechanical effects? So, as we can say now, as we would always think in modern physics, if something exists in physics, it should carry both energy and momentum. And if we think of light beams as particles, that's natural for a corpuscular theory, but it is possible to frame wave theories in terms waves carry energy and momentum. But the actual connection of that, the idea of wave mechanics, was only properly developed with quantum theory in the 20th century. So there was a bit of a conflict. If you're going to use energy and momentum of light, you're sort of inferring that it probably has a particle nature. So Kepler talked about the mechanical effect of light to explain the observation that a comet tail is always pointing away from the sun. He says that there's a solar wind of light particles that's always pushing the comet tail away from the sun. And so that's, the early 1600s. Descartes, a few decades afterwards, explains, and it's true, although Descartes made a bit of a mistake in his explanation, that Snell's law is actually a manifestation of momentum conservation of light. A little known fact, but actually quite important, is that, of course, if light is a particle, it should be affected by a gravitational field. And that was observed by Soldner in 1802. It's just that was also the year that Thomas Young demonstrated, as we'll get to, that light is a wave, and so waves were seen as different from particles, so it was completely forgotten that even in the classical world, gravitational deflection, light rays should be deflected by gravity, and it was seen as something that was a qualitatively new prediction by Einstein for general relativity, although actually it's becomes just a quantitative, and Einstein's calculation actually involves both the Soldner part and then a time dilation part coming from special relativity. Following on a little bit later on, circularly polarized light obviously is light where we get to polarization presently, But if it rotates around, Poynting, I've got to mention him because he was the first professor in Birmingham, observed that this should have an angular momentum that should be able to be transferred to matter. And although he couldn't quite do the experiment, this is routinely done now via the idea of optical tweezers that was developed by Arthur Ashkin in the 1980s and got the Nobel Prize for Physics a couple of years ago, or shared in it. And in fact, I'm en route to a big international meeting in Finland, which is on purely the angular effects of light. So the optical angular momentum, and so this is a major field in modern optics now that you can actually use light. Not necessarily here. I've drawn a picture of a solar sail. That could be true as well, but actually to pick up and manipulate small particles, such as biological particles, light is actually a lot better to do use than any other form of mechanical device. So that's so mechanical effects. They're visible when light interacts with matter, like reflection and refraction. And of course, historically, we can't think about mechanical effects without asking what is the material that light's propagating through. Famously and confusingly, people talked about the ether, in particular Newton, as this hypothetical material that light propagates through even in a vacuum. And in a sense, over the centuries, ether physics became a wackier and wackier subject as everything that was unexplained to do with light became a mechanical property of this mysterious ether. And here's a quote from Lorentz, 1916, so well into what we would think of as the sort of 20th century. "I cannot but regard the ether, which can be the seat of an electromagnetic field with its energy and vibrations, as endowed with a certain degree of substantiality." So even then he believes in the ether, however different it may be from all ordinary matter. So moving on to waves, and again in antiquity, but through to Galileo, 1610, people were very familiar with the idea of waves in sound. Pythagoras himself talked about sound as a vibration and as a wave. And so that's a sort of reference when people are thinking about light, is light a wave, they're sort of comparing it to sound. So in 1665, Grimaldi did various experiments where he noted at the edges of shadows, you see fringes like this. Of course, it's easy to see this with a coherent light source like a laser, far harder if you're doing it with sunlight or candles like these guys. Gregory in Scotland, 1675, used a bird feather as what we might now see as a diffraction grating and saw an interference pattern, although I couldn't find a picture. But importantly, Hawkins in 1678 proposed a full wave theory of light where secondary waves start on wavefronts of primary waves and you add the waves together. It's not incredibly quantitative, but it did a good job at qualitatively describing a lot of patterns, and Fresnel in 1818 picked up this and came up with a formal mathematically rigorous theory that we now recognize as the formal diffraction theory that agrees with all observations. But that wasn't seen as compelling. Newton himself talks about light as a corpuscle and has some explanation of why Grimaldi sees his fringes. And somehow it wasn't until, as I say, Thomas Young, 1801, who demonstrated interference from 2-point sources. Now, people always talk about Young's slits. Young didn't actually have slits. What he had was a very thin sheet of card, but actually using a laser and one of my hairs, I think I should be able to demonstrate it to you. And if I can't do it, no, it's not. The screen's not quite right here, but if you come to me in the break, I can show you. It's very easy to see a Young-type slits just by looking at a laser beam diffracting around a human hair. So this led to everybody overnight suddenly accepted the wave theory. And that was Young's later on more careful sketch of interference. This is a calculation I made analogous to that, including the direction of the wave itself, the local propagation direction, which would be what Newton would have said is the flow of the corpuscles. And interestingly, just 10 years ago, the group of Ephraim Steinberg in Toronto actually plotted exactly, or measured explicitly, these arrows as photon paths. So somehow the idea of photons as particles coming back can be used to explain this young diffraction pattern as well, that waves and particles really are dual. But now we've got waves everywhere, from quantum mechanics to gravity, and here's James Jeans, 1930, tendency of modern physics is to resolve the whole material universe into waves, and nothing but waves. Waves are of two kinds, bottled up waves, which we call matter, and unbottled waves, which we call radiation and light. We can reduce the whole universe to a world of light, potential or existence. The whole story of creation can be told with perfect accuracy and completeness with 6 words, God said, let there be light. Now, I don't quite agree with that. It's not quite right, but I'm not going to say any more about light waves. Instead, moving on to color, and Newton had his prism experiment, of course, which separates out the colors, refuting Aristotle that said the only true color is white. Newton's proving that white is made up of these colors, but these colors aren't necessarily made up of other colors. Of course, that's spectral colors, and we have a slightly more complicated story with color mixtures that I'm not going to go into too much. It's also interesting to observe, going back to the analogy between light and sound, although Newton didn't think that light was a wave, unlike sound, his definition of the color spectra, or the color hues, are red, orange, yellow, green, blue, indigo, violet, was inspired by the major scale. So red to orange, or orange to yellow. So red to orange is a tone, orange to yellow is a semitone, and that's why orange and indigo, which often don't seem to quite fit in, are there because he deliberately included them as semitones rather than tones. So he said color mixtures, but later on people realized that this isn't the full story. And of course it's also interesting that in our eyes we join together red and violet on the color circle, but actually on the spectrum we go off on each side. And Émilie du Châtelet in 1737, in I think the first publication for the Paris Academy written by a woman, proposed that actually there's light beyond red, infrared, which she calls heat rays. So identifying the spectrum was wider than just the visible spectrum. So color, again, it's Thomas Young and picked up by Hermann Helmholtz. Color is all to do with, what we see as color is all to do with our eyes. So this is Helmholtz's picture. It's a modern picture. Really, this is the sensitivity of the 3 types of cones in our eyes. And again, you can see the red and the green cone very close to each other, and that's, again, because it was a mutation in relatively late in the development between monkeys and apes in our timeline that actually separated these two. So it's not very strongly separated. So when we put it together in the physiology, we turn the spectrum into the circle, and this is the technical gamut of saturated colors. If you're playing on your computer, you'll be more used to thinking about the RGB color cube, where you can change the amount of red, green, and blue, which are related to these 3 peaks here, or magenta, cyan, and yellow, if you're thinking about inks for your printer, because one's writing on white, one's writing on black. And if we look down the axis of the color cube, you can see that we recover the, recover the color circle here, red, yellow, green, cyan, blue, and magenta, just on there with the white in the middle with all the colors. Rainbow is putting together these ideas. Descartes, 1637, this is his picture. He gets most of the rainbow as an explanation with what he described before. It's to do with reflection and refraction in a raindrop. In fact, the rainbow itself is a caustic. As you take the rays going up, the ones going out, they go down and then back. So that caustic is actually what you see. It's slightly different for different colors, of course, but you also get, if you do it with the wave theory of light, as explored by Airy and Stokes in the 1860s, some fringes underneath the rainbow, which come from actually the diffraction theory of caustics. And just relatively recently, in 1990, using photometry, people were able to actually measure what are all the colors of the rainbow. So this is measure of the rainbow, and here's our color gamut. You can see actually it's really only a very tiny bit of color space that the measurements of the rainbow actually give it. It's just we see all these different colors because all those colors in a very desaturated form occur very close to white. So I'm almost out of time, and I don't have time to tell you about polarization. I just want to very quickly say it was, again, discovered in a chunk of crystal called Iceland spar, and suddenly no one's got any explanation for why do you suddenly see, when you look through it, two images of what's behind rather than one. And Newton has an explanation. Have not the rays of light several sides endowed with several original properties? So that's from the ray theory, or the corpuscle theory. Hawkins also has a very detailed, complicated explanation based on the geometry of ellipsoids, but also accounts for it. I'm not going to be able to talk about it. I just want to show you one very particular thing. So obviously we've got polarizers. The main thing in natural light is light could be fully polarized, unpolarized, where you don't see any difference, or partially polarized. And different sorts of things are polarized in different ways, and obviously we have Polaroid shades to reduce the glare from the partial polarization coming from reflection. But what I want to finish with is the idea of what about the blue sky? Everybody who's ever lived probably has seen the blue sky. It's blue, I didn't talk about that. Rayleigh explained why to do with Rayleigh scattering. But it's also polarized. Here's me demonstrating it with a polarizer. You can see as I rotate the polarizer, the same patch of sky, it goes darker and brighter. I tried to fix where I thought it was darkest, and the line is what allows, so that's the polarization, dominant polarization direction there, and as it happens, the direction of the sun was off in that direction. Now, this isn't new. In fact, von Frisch, who got the Nobel Prize for Physiology and Medicine in 1973, realized bees see this polarization pattern. And I'll show you, if you come to me in the break, I'll show you this beautiful quotation. Once again, bees appear to us miraculous. It is now clear ants, other insects, crayfish, spiders, all perceive polarized light and use it for orientation. Amongst all these, the human being is the unendowed one. Physiology of our eyes. Nevertheless, working with some colleagues a few years ago, we measured the skylight polarization pattern. And this is the full sky. So angle from the zenith is radius here. There's the sun. And you can see that there's this funny sort of fingerprint pattern here, which is what we would call, well, what people in modern physics would call a half vortex. I think it still looks a bit like a fingerprint, but it's a bit like the optic axis of a crystal. And historically, these were discovered by people like Fresnel, Arago, and Brewster in the 1800s, but no one actually plotted the polarization pattern. So David Brewster said, "It is not one of the least wonders of terrestrial physics that the blue atmosphere which overhangs us exhibits in the light which it polarizes phenomena somewhat analogous to those of crystals with two axes of double refraction." But I want to just leave you with this picture. If our eyes had evolved to see polarization, we would see this fingerprint pattern whenever the sky is blue. there would be mythology about it. There would be love songs about it. There would be poetry about it. But it wasn't until 20 years ago that we actually went out and measured it to see what it really looks like. So again, just to show that there can always be features of the classical world or beyond the classical world out there if you know how to look. So we've seen various theories and approaches made to explain the empirical qualities of classical light, rooted in the 1600s. These were my themes, but that was just me. Interwoven with the physiology of vision and imaging technologies, anticipations of contemporary optical science and beyond. Sorry for overrunning, and thank you for listening.
Thank you very much, Mark. That was a whistle-stop tour on physics, physiology, technology, science. Without further ado, questions to Mark. We will try and keep to timing so that we don't eat into our next speaker's presentation time. So if you could just raise your hands if you would like to ask a question, and then we will try and get the microphone to you. Yes, over there at the top right-hand corner. Could you? Are you? Sorry. Yes.
Thank you. Yeah, I was a bit confused. Thanks for a whistle-stop tour, by the way. Amazing. I was a bit confused by that theory about, the light knowing where it was going to end up, and you said that it's trying to maintain something constant. Could you just elucidate that?
So what it is proposed as let's say, as a mathematical explanation for why light behaves the way it does. So you can say that if the light starts, so think about reflection, right? Reflection from a mirror. So if I have light that I know it starts here, and I know it's going to finish up here, and I say it's going to go in a straight line but bounce off the mirror, which path does it take? So we know that angle of incidence equals angle of reflection, even if those 2 points are at different heights. And that angle of incidence equals angle of reflection follows from the assumption that that's actually the shortest path, or the path that takes the least time. Similarly with the Snell's law, with this path and the sign of the angles and so forth, it follows from this assertion that it's the path that takes the least time. Now, obviously, this isn't a theory that explains why it is, but it's a principle that is consistent with the observations. So it's a bit like Kepler's laws of planetary motion. Kepler's laws of planetary motion says that the planets follow ellipses. It doesn't explain why.
Thank you. Cheers.
Thank you. Any further questions? There's one at the front, and I'm just trying to, and somebody on the left. So shall we take them one and two just to minimize the time lost in moving the microphone?
Thank you for a fascinating presentation, especially the way you categorize those 5 topics. Interesting. Would you agree that when you presented so many historic research, some of them were really unselected, and some of them started acting as cumulative science? Would you say that it is therefore evidence coming out of them that acts as the criterion for selecting science, rather than our consensual approach?
Well, I think it's a complicated question to answer, but I think what we can certainly see from certainly our modern perspective, and I was very much not trying to present anything other than with a whole amount of hindsight, is that certain observations, as I say, like Thomas Young, overnight, this debate that had raised for more than 2 centuries suddenly was immediately put to bed, so much that no one investigated gravitational diffraction of light. But other things can go relatively unnoticed, even in relatively famous books like Newton's optics, that there are features of Newton's optics that were not picked up until quite a number of years later that, again, would have resolved things.
Thank you.
Hello, Mark. Well, since you embarrassed me twice during your talk, I'm going to have a go at getting my own back even before the end. So, but bravo for doing such a good job of trying to get the history right of, Émile du Châtelet, rather than William Herschel, for example. But just to finish the precedent story, Snell's law. We now know this is Ibn Zal, right?
Right.
Okay, so
I was just fitting it into my Eurocentric
yeah, I mean,
story,
so there's this gorgeous trigonometric diagram before the end of the first millennium from Baghdad of what's
in light of the previous question, what doesn't seem to have been that familiar in Europe. So Kepler himself, he has a correspondence with Harriot in England about it, but he doesn't put it into his book, and that's
right. No, and Harriot, but I like Harriot's annoyingly published nothing till far too late. Silly man. But no, the one thing you said that I felt really raised my eyebrow because is all the colours of the rainbow statement, because you seem to suggest that the rainbow colours were in one tiny bit of the colour gamut. But they really aren't.
So these are them. Okay. So all I'm saying. So these were. So I mean, these aren't my measurements, but I've discussed this with the person who made the measurements. So he has. I mean, he's been making these measurements over 30 years of using detailed photometry, looking what part of the color gamut they measured on the sort of from his own measurements. And from his own measurements, although the range of colors does change, it is quite narrowly focused around the...
Well, just for one thing, there's no such thing as the colours of a rainbow. There's a three-parameter set of rainbows.
Sure, absolutely. So what he has is that he has in his measurements, he has a patch of the colour gamut that corresponds to his patch of his photograph.
Okay, cool.
I can show you the paper.
I'll pop something in the end. Final little question. Human detection of polarized light. What's your view on Heidegger's brush?
I think so I've discussed this with biologists. Heidegger's brush would appear to be a physiological anomaly due to the way that the different sorts of cones are packed in the retina. So it's not.
You don't think it's a detection of polarization?
Well, it detects polarization, but I think it's an accident rather than a relic of something that we evolved to see in the past. But I've discussed it with biologists.
If you could just pass it on to your neighbour, thank you.
Well,
and then after this question, we'll probably have time for one more.
The polarization. Thanks for the beautiful picture of the polarization of the atmosphere. I was just wondering, do we know what's causing it? Is it the gas or is it water? or?
Sorry, because I'm talking about history, I don't have time to talk about physics. Yeah, so it's purely explained by Rayleigh scattering. So the person who, So what we have, what causes the blue in the atmosphere is light coming from the sun, and it scatters multiple times, bouncing off different air molecules. If it was if it went straight through, we would see just the sun and nothing else. If it bounced once, so the point is the polarization tends to favor the direction perpendicular to the plane of scattering. So if the scattering is in the horizontal plane, it will tend to get more vertically polarized. So that would mean if it just bounced once, that you get concentric circles around the sun. Okay. But the symmetry is broken. There's a lot more atmosphere to the sides than there is this way. This is about 8 kilometers deep. This is about 300 kilometers deep. So there's a lot more secondary scattering. So net in the direction of the sun, it's vertical. So mathematically, and it's beautiful, you do a perturbation theory, the circles get perturbed into confocal ellipses.
Okay.
And you're looking at the focus of an ellipse.
Well, I was just wondering, so it's just the number of particles it scatters off. Like I was wondering, because you said a lot of creatures underwater can see polarized light, so as well.
So this would be, so it's different, so different would be, so the only thing this requires is the atmosphere to be optically thin.
Yeah.
So if it was thinner, there'd be less secondary polarization. So I've looked, but NASA never did it, is make a measurement of the Skylight polarization on Mars. But what we'd expect to see would be it's far closer to the concentric circles than confocal ellipses. But just to say, one of the things that people who do atmospheric measurements, like to say my colleague Raymond Lee, who made the rainbow measurements as well, the dependence of the sort of particular distance from the sun of these points is dependent on the number of pollutants in the atmosphere. So they actually do use this polarization pattern as a very quick way of estimating pollutants, for example.
Right, we've got time for one final question back on the left.
Like you said, historically, intuitively, what things like as like a straight line, but can this be manipulated or played into other shapes, geometry, like in optics, like you could try out?
So good question. In modern optics, absolutely. So the first point to say is really like follows the path which makes the time the least. If we're in curved space, then obviously it's not necessarily going to be a straight line. And in fact, in the last 20 years, people have realized that you can engineer materials, metamaterials, through something called transformation optics, where you can fool the light passing through a material into thinking that space is curved. This was the basis, for example, of invisibility cloaks that were in the news about 15 years ago and continue to be an area of intense technological development.
Right, well, thank you very much. Thank you very much, Mark, for this brilliant introduction to the rest of the proceedings for the day, giving us such a concise but quite wide introduction to a range of topics that will interest us both this morning and this afternoon. Thank you. Well, it's a great pleasure to welcome Professor Olaf Müller from the Humboldt Universitat in Berlin, who is going to speak to us, well, he's going to give us a brief history of color metaphysics. So 30 minutes of a presentation and then 15 minutes for questions. Thank you very much, Olaf.
So thank you very much for the invitation to this fascinating conference. When I got the invitation from Joanna years ago, I was puzzled because there occurred to me to be some kind of misunderstanding. She asked me explicitly to speak about color metaphysics, probably not knowing that I had been resisting the tendency to do metaphysics all my academic life long. So I come from a tradition where you just don't do metaphysics because metaphysics is bad. So here is my pessimistic meditations about metaphysics in the subject of color. And the main problem I have, I mean, I did a lot of research about color during the last 15 years. And there's this principle, never trust a skinny cook. And I would translate this into philosophy of color. Never read a book about the philosophy of color which doesn't have color plates. And that excludes an enormous amount of the literature that somehow pretends to do something with colors, but they do it with their eyes closed. And that's a dangerous tendency in metaphysics where I want to try to resist. So what's metaphysics? The notion is pretty old. There's a book by Aristotle about metaphysics. He didn't name it himself like that. And a librarian who was puzzled where to put that book into the order of other books by Aristotle called it metaphysics, the book coming in the order now, after physics. That doesn't give us an answer what this crazy discipline in philosophy is all about. It's a super abstract discipline, and I'm one of those philosophers who is frightened of abstraction. We like the concrete. Now, the first questions in metaphysics that you will all know is, for example, what is there? For example, is there God? And if she exists, what kind of properties does she have? Or do we have an immortal soul? Or are we free? These are classical questions from metaphysics. But I believe colors cannot come into the picture here because they aren't as important as God, freedom, and our soul. So what could be another interpretation of what's meant by this issue, metaphysics of color, is maybe something ontological. So when we look very carefully at the furniture of the universe, what is there and what isn't there, then the question arises if colors belong to the furniture of the universe or not. Now, perhaps that's a bad question, and liking the concrete, I would translate the question into what difference would it make if there were colors as opposed to if there weren't colors. And maybe it makes a difference in painting. So for example, if you degrade colors and push them out of the furniture of the universe, out of the things that really exist, then maybe you concentrate on drawing and color isn't that important then in painting anymore. And indeed, the metaphysics which was opposed to colors led to theories of art where the people did not much invest in the knowledge of colors and in application of colors. So there you see that metaphysics can be quite a dangerous business. In my second meditation, I jumped to the Middle Ages, and there were two competing schools, the nominalists and the Platonists. And the nominalists say that there's nothing but individual objects out there in the world, for example, this very table or that very rose. And their opponents, the Platonists or the conceptual realists, claim that in addition, there are other entities than these concrete individual things. For example, the tablehood over and above all the tables. So we imagine that we have many tables there. And for example, you could say they all are not quite perfect. They try to be the perfect table, but they are not the perfect table. And the tablehood is what tells us what a perfect table would be like. Or about the color pink, we could say we have all these beautiful pink roses, and then in addition to the pink roses, there's the property of pink, a certain shade of color, you might want to say. Now, it's difficult to say what it means to claim that in addition to the concrete objects, we have these abstract things out there. And nominalists just say, as we don't need them, let's get away with them and let's speak only about concrete objects. Now, when you look at colors, one way of operationalizing this issue could be, you could think if you take all the pink things and you scrape from all these pink things the first layer, the pigments which color them pink, right? You could put all these pink pigments into a big basket and you could say, there's the color pink. But obviously, this is not what's meant by the idea of Platonism with respect to colors. When you want to claim that there is the color pink in addition over all the concrete pink objects, there's something more mysterious in this claim, and I confess I don't understand it. The third meditation is something which is still more dangerous about colors. So I go now to early modern ages when there was color research done in the sciences, as we saw in the first presentation today. And then there came up such an ideology that we have some qualities that are grounded in reality as reality really is, and then some other qualities are merely grounded in human perception. So they depend on the coincidences of our biological makeup. And some of these primary qualities, which were supposed to be the basis of what we do in physics, could have been the quantity of particles. So you imagine little particles and you can count them, and it's really objectively given how many particles are, let's say, composing a certain table or something like that. Then what's objectively out there, what's a primary quality, you could speak about the geometrical shape of the particles. Maybe they are round, maybe they are cubes, or what have you. You could also speak about the objective arrangement of these particles in space. It's some geometrical quality which you might speak about. And you could also put them on a scalar and you measure their weight and you have the mass of these particles. So the physicists like to think that reality is made up of objects which have these objective qualities. They call them primary qualities. They are first out there. And then in the next move, they said, well, secondary qualities, that the bad stuff, that's what isn't really out there. That's what is made up by the human mind when you look into reality. And one of these things is the taste. So the particles themselves are supposed to have no taste. And when we have this beautiful cinnamon taste, it is made up by our mind and by our tongue. The interplay of the particle, the tongue, and the mind creates the taste, but the taste isn't out there in the world. Atoms don't taste like cinnamon, for example. And then the same is being said about colors. The colors aren't out there. What's out there is, we could nowadays say photons. You might say light rays of a certain wavelength. And they have these properties. The wavelength is a mathematical property. We measure it. It's, let's say, 600 nanometers. This appears green to us, but that is a human addition to what's out there in the world. In the photons themselves, there's no color. We could speak shorthand about the color of photons, but what it means is, in fact, a certain wavelength. And Newton, of course, was the master of mathematization, and his optics was the attempt to put mathematical numbers instead of the colors. He wanted to get rid of the colors, and in fact, when he improved telescopes, that was one of his main moves to get away with the disturbances of colors and let's put them into numbers and let's have them secondary. There's more qualities that then are accused to be merely secondary, for example, beauty and goodness. All this is projected back onto the human being as though there was no objectivity about morals, no objectivity about aesthetics, no objectivity about colors and taste. This is a dehumanization of many human experiences, but it was a good principle for doing science. The question is if it's a good principle for doing philosophy or metaphysics. Now there's one danger in this. When you start wondering about it, for example, in the list of the primary qualities, where you have a lot of mathematics, mathematical properties are liked by this ideology, then, of course, the question arises, is mathematics something done by humans, or is it somehow objectively out there? And the objectivity of mathematics is a highly disputed issue in the metaphysics. Are there really the numbers out there on the Platonic sky, or what's that? For example, you might say the numbers are given to us by God, and the rest the humans made in mathematics. So there's a lot of discussion. But as soon as you increase this tendency against secondary qualities, the danger is that also mathematical properties and everything might be swallowed up by the human mind. And the tendency leads us to an idealism, which could be interpreted as saying that perhaps all qualities and in the end all objects are merely grounded in human perception or in the way the human mind is organized. Perhaps there's nothing real out there. So you see, I believe, what the dangers are in metaphysics. And now, having seen all this abstraction, I would like to jump back to an idea that one might call naive realism. Goethe was one of the champions of that in the last century. Hilary Putnam, great philosopher from Harvard, went into different directions. The late Wittgenstein had some such ideas also. And there were opponents in this debate about colors now, Schopenhauer and Berlin and Kay. And the idea is here, naive realism is a realism with a human face, you might say. Things are the way they appear to us. Things really are that way. Of course, the rose is really pink. There are millions and millions of colors. And when we come back and say, well, all the things which we were talked out before are indeed existing, then the life gets nicer, the philosophy gets more colorful, and then you can, of course, start wondering which are these colors which are out there in the world. And physiologists keep telling us that we have the capability of distinguishing 2 or 3 million different colors. And then the ethnologists went out there into the different cultures and gave the people color plates. This was the set of colors they handed over to the natives, and then they asked basic color terms, and they should find out which is the best representation of, for example, what in the native language would be red, and so forth. And the issue was if this is culturally relative or if there's some stability in human perception so that in different colors we might agree on what is the perfect example of red or the perfect example of yellow. And interestingly, these researchers found that there's a lot of stability across cultures, much more than one would have thought, relativistically speaking. And they came up in the end with 12 colors. Some cultures have only 3 or 4 or 5, but the first 3 or 4 or 5 are the same in all cultures. That was the claim. And when you look at the possibilities of really saturated colors, you get a beautiful amount of, for example, 60 different shades, which are all equally far away from one another. I see that the projector isn't that normal because the yellow comes out a little too dirty. And just when I spoke about that there could be perfect examples of some color tones, I wanted to remind you of the quarrels you have in your family and with friends about if this is now a really good green here or if it's not. And I would like to say, of course, there's a lot of individual aspects in the personal perception of colors. But when it comes, for example, to the color of yellow, we pretty much agree what is the perfect yellow and what's not. So I do it with my students from time to time. I make a competition. Everybody is supposed to bring the yellowest object to class. On a sunny day, we have to do it because otherwise one can't see enough. And then they bring tulips, and they bring books, and they bring other gadgets, knives, and so on and so on. And then I lead that discussion, and of course I have a lot of authority over my students, right? And I say, but could we agree that this object here is a little too orange, or a little too dirty, or a little too pale, and so on? With my authority, and of course I pretend to be nice to the students, with my authority guiding this discussion, we pretty quickly can agree that there's the one yellowest object and everybody agrees which it is. It's quite interesting that there's not much about taste here or individual variations. The perfect yellow, we agree easily. And by the way, interestingly, in the case of yellow, this game goes the easiest. When it comes to green, it's already much more difficult. Now I have here an example of something which I called for a while the perfect blue. This is a Berlin blue, which was created by alchemical accident. So an alchemist wanted to produce gold, I believe, and instead he got the first pigment that's not natural. We could discuss how blue is it really. And I brought you here a color circle that attempted to sort out the most important 6 basic colors. So you have down there a green, then this yellow again. I think it's a bit too greenish now. We could agree it's not yellow enough on this projection. Here on this computer screen already it's much better. The red is here a little too dark, and then comes the cyan and the dark blue. And on top of it is a color which in German we like calling purpur, but the English translation wouldn't be purple, I think, but one should call it maybe magenta. And that is a mysterious color because in Newton's spectrum it doesn't occur. And when he bent his color wheel, he was quite at a loss about what to do with this. And to this I come now in the 5th meditation. So when you come up with such color circle like this, you will want to know how many colors do we need to postulate. How many colors are really there and how many of them are maybe only a mixture. So we have always this tendency when we speak about metaphysics, we want the number of items as little as possible. We don't want an abundance of chaos. So if we have 3 million different shades of color that we can distinguish, the question is, can we reduce it on a small amount of colors, which would then be the basic colors, the really importantly existing colors. And in Renaissance painting, the painters came up with 3 colors. And the idea was, it's a bit similar to when we speak about, are there really tables? Well, physics tells us there's no such objects as tables. The tables, they are consisting of electrons, protons, and neutrons, and they are complicatedly arranged into the shape of a table. So the real stuff is these 3 things. And tables exist only in a derivative sense. And now, when it comes to painting, the Renaissance painters came up with a similar idea. Instead of painting the abundance of colors which attack us as we go along in the world, they tried to find pigments such that they need very little of them in order to mix everything else from it. And they came up with the idea that there's only 3 primary colors, and they are here the uppest color, the magenta, then the yellow, and the cyan. With these 3 colors, you can mix more or less all the colors that exist when you have paints. So you need pigments, and you can mix brown, you can mix black even from this, and you can mix red, dark blue, and green also from these pigments. Now, Newton when he was fighting to get his optics pushed through, it wasn't accepted from the start. So he came up with the first publication in 1672, and the people didn't believe him a word that he detected the primary colors in the rainbow spectrum colors. And the people were not wanting to believe it because Newton suddenly said, well, the white light consists of infinitely many different colors in this rainbow spectrum, infinitely many. This was too much for quite many people who wanted to reduce entities. And then Newton was a bit in a bad situation. He needed support, and as he knew that the Renaissance painters had been reduced the abundance of colors on 3, he also tried to come up with 3 primary colors. So when you read his books and the question is how many colors are in the spectrum, some of his statements say there's infinitely many, and in fact that's the official doctrine which we believe now. But quite often he said it's 7 colors due to this music analogy, which is a very bizarre analogy. Sometimes he says 5 colors, and then he quite often, when he wants to join forces with the artists, he says it's 3 colors. And these 3 colors we know from our computer screens. So when you mix light rather than pigments, you must obey other mixing rules. This was not known to Newton's time enough. But you can say with Newton there is no real brown, there is no real white, there is no real magenta. All these can be mixed up from 3 primary colors from the spectrum. And these 3 colors are not the 3 which you need for pigment mixing, which was magenta, yellow, and cyan, but for the mixing of light rays, in order to make up all the colors on your screens, you need red, blue, and green. And that is the so-called additional, now how does one say, additive mixing of colors. Now, that could bring us to the idea that there is really no brown, and there is really no white, and there's really no magenta. Particularly with the magenta, I think, there is some point which we need to discuss now, because magenta is an important color, and it is all the time downgraded by physicists. And when we speak about the metaphysics of color, I want to now propose that magenta is in much better shape than the physicists would like to have it. Here you have the substructive color mixing as we know it from painting. And here we have Newton's first experiment, which you showed us already in the first presentation. The light ray is split by the prism and gives us the rainbow colors. Here is a photograph of such a spectrum, and you see that the spectrum ends on top of it with a very dark blue, which goes away into black, quite beautiful. The black is not considered part of the spectrum, it doesn't exist. And down there you have a beautiful red, like in a ruby. Is it called ruby or ruby? I don't know. Ruby, thanks. And it also disappears into black, but there's no magenta here. And the Newtonian idea about the magenta is that the magenta is a mixture of many colors of the spectrum minus the green. So if you mix all the colors of Newton's spectrum, you get white. So white doesn't exist by itself, it's only a composition. If you take out the green elements from the white, you get the complementary color of the green, and that is the magenta. So magenta isn't out there in the world, magenta is made up by the human mind. And now I want to reopen the case of magenta, and I want to do it with the help of Goethe and a little help from contemporary quantum mechanics. This is a bit speculative, which I offer to you now. The 5 pessimist meditations are over, now comes the good news. And when we agree on that magenta exists only in this derivative sense, as it's made up by the human mind, mixing, let me say, on the retina, all these photons arrive, minus the green ones, and then our organism creates the impression of magenta, then we might want to see what Newton did to this magenta. So I came up now with a different version of the color wheel than you showed us. So Newton took a spectrum. It depends a little on the material of the prism, and I have assumed a water prism because with water we can best replicate the experiments nowadays, as we don't know quite what the Newtonian glass was made from, so let's do it with water. Newton used water also, so we can make the spectrum. And in some sense, artificially, he made proportions in the spectrum on the space of his screen. And he did it according to musical harmonies. But I must correct the presentation before, because he doesn't do it with C major, and he doesn't do it with the minor harmonies. But when you look at the piano, he does it with an old church harmony system, which is Doric, I think it's called maybe. When you go on the piano from the D to the D, the half tones are somewhat different than when you go in major. And that's how he did it. I would love to know, maybe somebody knows in the audience, why he didn't choose major or minor. Because in Newton's times, these two modes of making musical harmonies was already quite established, while the church tone systems of harmony were already sounding old-fashioned. So it would be interesting what kind of music was Newton listening to, why did he come up with that? But quite artificially, he divides it like that, and then he rolls this color wheel on it, and here, between the blue and the red, you have the D, where it comes back to the beginning. You are up for an octave then. And that's there where the purple or the magenta color is supposed to be, but in Newtonian optics, it's just not there. It doesn't exist in reality, according to Newton. Now, Goethe was famous as a poet, and he was famous as a lover, but I'm not quite sure how much it is known outside the German-speaking world that he spent most of his time doing scientific experiments, and most of the time he did in attacking Newton's optics. Everybody tells us in high school in Germany that this was a mistaken and completely misguided attempt, and that was also how I started when I went into color research. And then when I got into the details of his attacks on Newton, I saw they described an experiment which in official high school physics does not occur. It's put under the carpet. And this is a version of Newton's original experiment. In Newton's original experiment, you have the dark chamber, you have the sun shining, you have a little aperture, and behind the aperture there's a prism. And the prism is lit only on a tiny, tiny fraction of its surface in a round circle that the aperture lets the light through. So you have a prism lit in a very precise dot, and the rest is unlit. Goethe now, the anarchist, decided to turn the tables and switch the roles in this experiment of darkness and light. So instead of having the prism lit in a very, very tiny area, he decided to open the window screen and put the prism into the full light of the day. And then he glued a tiny little wooden circle on that prism. And the diameter was the same as the round hole in Newton's aperture, which he had cut into the window shutters. So everything is the same in this experiment, only the light conditions on the prism is opposite. And what's super interesting, and before I saw it for the first time, I didn't believe it myself, that you also get a prism, a spectrum. You get a spectrum. And the spectrum is equally big as Newton's, it's equally beautiful, it's equally differentiated, but it's with entirely different colors. And namely, in the middle you have this magenta, which is missing in Newton's spectrum. And on top of Newton's spectrum you have the blue, and here instead you have the yellow. So it's the other way around, because in Newton's spectrum down there you have the yellow and red, and here the yellow and red is up. Now, when you look at this spectrum without a biased mind, you would like to say, I believe, that this spectrum has equal rights to metaphysical existence as has the Newtonian spectrum. So to the human eye they look equal. And it has been just a coincidence that Newton found his spectrum first, not the other one. If he had been not interested in astronomy, where you look at little white spots at the dark sky, but if he had been interested in biology and had looked through a microscope on little lice instead of stars, the lice are black and the biologists lit the surroundings white, then he would have come up with a spectrum first thing. And his attempt of improving microscope would have led him to take this as a basic thing and not the other one. So it's an historical coincidence with which experiment optics started. Now, Newton, of course, has an enormous amount of experiments, and not only this one. For example, he can join the colors from his spectrum back to white. And it's interesting that Goethe claimed that all the experiments that Newton did in his dark chamber can be repeated in the bright chamber, and everything gets the other way around. So when you take these colors and you reunify them, you will get back a black spot, interestingly. And so all the Newtonian experiments have a counterpart where the roles are switched. And that brought Goethe to the wildly anarchistic idea of claiming, just for the sake of the fun, that maybe not white light exists and consists of the different colors of the rainbow, but perhaps it's the other way around. Perhaps darkness exists and whiteness is nothing, as we now believe the other way around, and black would consist of these colors. Now, of course, this is totally crazy from a contemporary point of view, because we now have gotten hold of the photons, and the photons, there are no purple photons, there are no magenta photons, and that should put an end to this crazy idea. That was my conclusion ages ago about this, till I started more and more speaking with physicists. And suddenly I met two physicists who independently of one another developed a very nice idea, which is the end of my presentation now, which is this. The wavelength of photons isn't completely sharp. So because of quantum mechanics, it's a little blurred. There's a superposition of a few wavelengths in each photon. And the sharpness of the interval of which these photons are superimposed depends upon the time which it took to create these photons. So the photons typically are coming into being, I believe, in something like 10 to the power of -7 seconds or something like that. That's an ordinary way of making a photon. And if you take so much time, then of course the time is blurred, but the wavelength is quite precise. Now, if instead you shorten down the time in which you produce the photons on, for example, 10 to the power of -17 or -18 seconds, which doesn't happen in nature often, but in our laboratories we are now able to do it, then, according to uncertainty principle by Heisenberg, the wavelengths which are mixed up in this photon are all the wavelengths from 400 to 800 nanometers. So it would be a white photon until you force it to break the wave function, or whatever is the proper pronunciation here. Now, if you have a white photon, it's already interesting. You can make one particle which is white. Newton claimed that doesn't exist, and now modern physics tells us we could make them. They weren't made yet, but we could make them. And now these two physicists said, because I wanted a magenta purple photon, right? The physicist said, well, what we do is we send the white photon through a green filter, and then we force it to be in magenta's color. Now, I'm recently collecting money to get the thing done. I didn't do it yet. The physicists keep saying it would be easy to produce those photons, but it would be not that easy to prove that they have the wanted properties, one by one. So suppose you make many purple photons and you make them hit on a screen. It is supposed to look magenta, but you need quite many of them to create that impression. And the question now is, how can we prove that they were not many different photons hitting the screen on that spot? How can we prove that they were all the magenta ones? And this will be difficult. Maybe in 5 years you check out my homepage and then we might have done it, or maybe it's done already. Okay, thanks for your attention.
Thank you very much, Olaf, and thank you very much also for this exemplary timekeeping. Let me open questions.
So quite a lot of things you're discussing are really to do with the physiology of the eye. So the fact that we have 3 receptors, red, green and blue. I mean, you're showing us colours here, but actually it's all red, green and blue. That's all there is. So the magenta, for example, there aren't. Your example is amusing of how you can make them physically, but the real point is you can stimulate both the red and blue receptors in the eye. Even though you don't have photons that do that, you can have a mixture which does it, and that's magenta. So people may not have understood the physiology, but that is a lot of what's going on, and actually a lot of psychology as well. So when I was a child, we had an orange car, but under sodium streetlights it looked white because there was no contrast to anything. So a lot of it is to do with our physiology.
Yeah, right. There's a lot in physiology, but let me tell you, when we started this research to turn the tables and for the sake of the fun to say maybe black consists of all these colors, then the first step is, of course, to repeat all the experiments that Newton did and then what Fraunhofer did and so on, and always try to invert them. And at the end of the road, we would start discussing if with this different alternative, complementary physics, we might come up with a different theory of the human receptors in the eye. So, of course, the way we describe these receptors now depends upon Newtonianism. So we analyze and measure them on the ground of the theory of Newton and his followers. And this anarchistic end of my presentation was meant to make us reflect if there couldn't be an entirely different way of doing these things. And then, of course, the receptors, the case of the receptors have to be reopened.
1, 2.
Hi, so I think there's a sort of common thread between this and the so I'm going to really stir things up in a moment. There's a common thread between both this and the previous talk, which is that you're both starting with a spectrum. You've come up with a different spectrum to the previous spectrum. But isn't that actually isn't that suggest that the limit is because that's the starting point? So if I ask, I like the idea of your white photons. If I say, well, what's the colour of a rainbow? I would argue that you guys have all got it wrong, because the rainbow is clearly white. If you go and you look up in the sky, you will see a big white blob, and around the corner of the blob, sorry, not a corner, around the edge of the blob, there's a little coloured bit. And everybody goes, oh, pretty colours. But the colours are just the little chromatic aberration at the edge of the blob. So is it that we've somehow got focus is a good word, isn't it? We somehow looked at the spectrum and at this little blob, and that's kind of derailed, but that's kind of warped the whole way that we look at this, that we're focused. So the rainbow isn't a prism.
Yeah.
The colours in the rainbow aren't the same colours that you get in a prism, because the ones in a prism should be down to an exact wavelength. The ones you get in the sky are an overlap of the various bits of white. Sorry, I thought it was. Sorry, I thought I was using the microphone. Oh, sorry about that.
Okay.
So the colours in the rainbow aren't the colours in the prism, because...
Yeah. Okay, so I was interested in this exchange we had after the first session about measuring the rainbow colors. And I must say that from my observation of the colors of the rainbows, since I do the work with the spectra and with the prisms, I see that each rainbow is different, and I would like to get it more controlled. But I wanted to maybe reply to your question by way of pointing out that I got fierce attacks by physicists on our project from a German guy in Hanover, for example. The name is Zawisza. And he challenged us and said, there's two things that you will not be able to turn the other way around. One is the rainbow, and the other one is the Fraunhofer lines. So I asked him to publish this prediction because I want to repudiate him, and it will take some... and it is now published last year, his attack on this. And then I went to my physicist friends who helped me because I can't do the experiments myself. And to my surprise, they said, look, Olaf, with the Fraunhofer lines is easy. We will do that. Give us the money and we'll do it for you. The rainbow will be costly. And I asked how much money they need to turn the rainbow the other way around. That's not trivial, it seems. And they want something like 300,000 euro for that. And I'm busily now applying for the grant to do it. But let us say, at the moment at which we can turn the rainbow, your worry should be addressed, I believe. So it is true that the rainbow colors are not identical to the spectral colors of the prism, but there is some similar relationship between them. The rainbow is more complicated, and the spectrum done by prisms is easier to understand. So I shouldn't have maybe mentioned the rainbow because it was misleading into chaotic territory.
Maybe could I just add to that? I mean, because I think that one of the points about this that you mentioned is also actually colour space, if we're thinking about it, is for three-dimensional space. So you've got red between 0 and 1, green between 0 and 1, and blue between 0 and 1. There are different ways of putting coordinates on this colour space. So red, green, and blue is one of them. But what I try to do in my picture is say, if you look down the diagonal axis, you see the colour wheel is the angle. So it's the angle around that direction. So it's a bit like you're saying, well, you can't say that you're sort of north, south, east, west, very close to the North Pole. If you're at the North Pole, you don't have to walk very far between being due east and due west of the North Pole, because you're in the region of the space where all of the angles are very close together. So what it means in a physical term is, and I think this is what you're saying, the colours are all very desaturated, but the hues, the red, green, blue, they're still there, they're just there, they're a lot less strong than they are in the Newtonian spectrum.
Yeah.
Then this is the question that Tom asked me, whether this is actually really the case, and obviously one has to really measure the rainbows and see what is the saturation of the colours in.
Right. May I just make a short remark to this? When you look at the Newtonian color wheel, it doesn't go all the way as we see, right? Sorry, here is the attempt made to give all the colors from human perception. And interestingly, the top color is not present in the Newtonian spectrum. So it's just missing there. And I wanted to defend it and say that if metaphysicians say it doesn't exist really, I bring you experiments where I show you it does exist. So don't worry about purple.
There's a question over here. Could you pass on the microphone?
You said towards the end of your presentation that you wanted to look at it the other way round to see might be discovered, inverted commas. This strikes me a little bit like the old problem with phlogiston and oxygen, and they eventually got it the right way round. Do you really think you might get an added insight by what you're doing? That's one point. The other one is, what's happening now with the experiment that Alain Aspect used to be doing? I know this was with the 2 slit experiment, but it was to do with the, whether it's one or it's several wave packages, should we call them, because you got onto that wave package idea towards the end of your presentation. Yeah. So that surely relates to what you're talking about. And the other one was, it strikes me, this idea of whether you see something, whether it really is or it isn't, this is the early part of your presentation, it's a bit like the old problem of quantum mechanics, and whether you, let's say the Copenhagen interpretation, you only see it when you're looking at it, or it's only in existence when you're looking at it. Can you comment on these things, please? Yeah. 3 things.
First, as to this last question, I would like to say metaphysicians cannot bring knockdown arguments that one way of looking at these things is better than the other one. And it is a matter of human practice, I would say. If we come back to this naive realism where you just say everything is out there the way we see it, which is humanistic, or if we detach ourselves from our organisms so much that we trust only the equations done by physicists. But that's a big issue in metaphysics, and there's no arguments. It's just a matter, I would say, a matter of style of thinking. It's a matter of taste, of character, which option you choose here. And I'm glad now with the Goethe-Putnam solution, and but that's my personal makeup, I would say. And now the other issue, I just addressed the one thing about the Thomas Young and the double slit experiment, where we were convinced that light can be described as consisting of waves. And when you do a grating, no, is it called grating or grate? I don't know. Grating, yeah? Okay, a grating, and you send the light through, you get these spectral colors, you have some maximum in the middle, and then you have these other rainbow colors, and this looks very Newtonian and can be used in order to calculate the wavelengths of the different colors. So the simple geometry, you see where does the blue land, you know the distance of the stripes in this grating, and then you calculate it. And my opponents with this other theory, this fun theory, my opponent said, well, you cannot assign wavelengths to the dark rays which come from the Goethe spectrum. And so I asked my friends from physics if they could repeat that experiment the other way around. It can be done. So we can send a shade through a grating surrounded by light, and you get the exact color opposite of the original experiment. And then we can assign the wavelength of 600 nanometers to, for example, the magenta rays. And this craziness can be repeated can be prolonged for a long, long time. And I have not yet seen the moment where the symmetry between these two systems breaks down. Now let me say two things about why it was claimed by Goethe. Goethe did not claim that darkness is everything and white is nothing, so he didn't turn the tables around. He used it only to convince us that Newton's logic is flawed, because with the same logic Newton came up, he can claim with his experiments this opposing theory, and he said both are inadequate. What we should do, we should accept the true existence, metaphysical existence of both factors, darkness and light. They were making up the world of optics before Newton showed up. Newton was the one who pushed us into the dark chamber, claiming that in the dark chamber there's no optical effects minus this little light which goes through. But that was there was no reason for it. It was just Newton's style of doing these experiments, and doing them the other way around was neglected in the further path of history. Now, as I'm in Great Britain, I would like to add that in the beginning of 19th century, there actually was a scientist who claimed that Newton had got it all wrong, and that white is nothing, and that the darkness is the power of optics. And this guy, I don't know how much he is known. The name is Thomas Reid from Edinburgh. He was an eyes doctor and also president of the Physical Society of Edinburgh at the beginning of 19th century. He published one book. He promised two more, but they didn't appear, I think, and he published 6 to 7 essays about it. And he took it totally seriously, this theory, while Goethe did it only in order to attack Newton.
Thank you. One final question at the back, and then I'm afraid we'll have to close questions for this session. If you could keep the answer compact, please.
Thank you. That was utterly fascinating. Yeah, one slide just whipped past too fast for me to read the bottom. You mentioned Schopenhauer. What was his comment,
right.
Please? Thank you.
Yeah.
Cheers.
Okay, I forgot him. Sorry. So he was the guy who said that in all cultures there's just these 6 colors. So he had an early version of this basic color term theory of Berlin and Kay, but he said it's just 6, and he studied Greek language, Latin, and many other languages, and he claimed that there's an ideal color always, and then he connected it in an interesting manner to Platonism, saying that it is just these 6 colors, metaphysically, and really we never encounter them because our life here is too dirty and there's no perfection here. And even if you look into something that looks most perfect yellow, it's never the Platonic perfect yellow. We can only imagine this Platonic yellow, the ideal yellow. And one of the reasons why he was right, I think, about that, why one might go back really to this Platonism here, is that if you ask an artist to paint you a perfectly yellow painting, or if you make it on your computer screen, and you stare on it for a while, the impression that you see is not stable, because your human eye wants to get the opposite color. It busily works against this yellow, so it's never a stable impression. It is always vivid, and only if we had the very Platonic idea of the true yellow, it would be stable. Platonists wanted to have a stability in the objects and not this floating chaos in our dirty world down here. This is a metaphysical thought which I gave on the screen in order to please Joanna, because she wanted some metaphysics.
Well, thank you very much, Olaf, for this journey into the metaphysics of color. I think it's set up. So I'm very happy to introduce an academic who is at the other place in Berlin, at the Technische Universitat. Dr. Arianna Borelli is going to talk to us about rays to waves and beyond, light propagation in historical perspective. Thank you very much.
Thank you. Thank you so much. Thanks for the chance to be here. I am glad and honored to contribute to this historical overview on opinions on the nature of light. And I will focus on the period which goes from the early 19th to the early 20th century, with, in the end, a brief look at situation today. And the period I will focus on is one in which really important, one could even say radical changes occurred regarding the opinions on the nature of light. In the beginning, around 1800, there was a debate whether light should be conceptualized in terms of waves or particles. Then the wave opinion established itself, but then by the early 20th century, doubts had again come up because it had become clear that light sometimes behaves like a wave and sometimes like a particle. These developments were quite complex from the scientific and from the historical point of view. Many authors contribute to them, and it's not possible for me to do justice to all of their work. What I did in my presentation is to focus on some episodes which we today regard as important for this story and discuss them a little bit more in detail to give you an idea of the questions being asked and the answers being found, and to give you also an idea of the broader developments. But many more authors contributed to them, so please do not think that only the authors that I mentioned played a role in that. And in this spirit, I decided to start my story with a series of experiments conducted from 1800 onward by the British astronomer, actually William Herschel. These experiments are about what Herschel called the invisible rays of the sun. And what Herschel did in this experiment was to explore the possible connection between sunlight of different colors and heating power. This was a connection which, of course, that there is a connection between light and heat is obvious from everyday experience. It was always known, and it was always a part of the disputes about the nature of light, whether light and heat should be seen as two different things, for example, different particles or different waves, as we already heard. But what Herschel wanted to look more in detail into was the possibility that light of one color heats more or less than light of another color, which of course seemed to indicate a closer connection between light and heat than possibly assumed. And I should say Herschel, as I said, was an astronomer, so he was not primarily making experiments about light. He was using light as a tool of research to investigate the stars and celestial bodies. But he had, in his astronomical research, become aware of this possible connection and decided to explore it more in detail with an experimental setup, which is what you see there. This is an image from somehow later paper by Herschel himself. The experimental setup is quite simple, and we just talked about sunlight and the color spectrum. Here, as you can see, there is a window which is closed except for a slit. Through the slit, sunlight comes in, goes through a prism, is decomposed into its colored spectrum, which is projected on the table, and Herschel very schematically represented it and put also the names of the colors near it. And what Herschel did was to take a number of thermometers. As you see there, these are thermometers mounted onto wedges, and in his original experiment, he positioned the various thermometers with their bulb, the sensitive part, in correspondence to the different colored stripes, waited a bit, and then noticed that indeed the temperature in all thermometers rose, but it rose more in the thermometer that was placed on the red line than, for example, in the one that was posed on the blue line. So the connection between color and heating power was experimentally demonstrated, but what was even more interesting was that in his first experiments, Herschel noticed that if he positioned thermometers, as you see in this picture, above the visible spectrum, so where you would say with your eyes, oh, there is no light there, still the temperature in the thermometers would go up, and it would go even more up than with colored, with visible light. Of course, for us, this is clear, that's infrared light, that's, it's really powerful, it has a great heating power, but for the time, this was a rather surprising result. And Herschel interpreted it quite correctly by thinking that sunlight contains not only the visible colored light, but also some rays which are invisible, at least to us, to the human eye, but still can be detected thanks to their heating power. So invisible light, and here just let me underscore this point. Until then, as has been also said in the previous talks, light was maybe mysterious in its deeper nature, but as a phenomenon, well, it's clear light is something visible, it's bright, it's opposite to darkness, and then now you have invisible light? What is this supposed to mean? These experiments were repeated by other authors and confirmed, because as you can imagine, this was not something that everybody accepted immediately. But it was somehow one component in the switch which led to the establishment of the wave theory of light. Now, I have here to qualify a little bit a statement made by previous talks. Yes, indeed, the wave theory of light became established during the first half of the 19th century, but it was a rather slow development. The young experiments, which have been already described, played an important role in this context, but they were not really accepted by everybody overnight, also because, of course, at the time it took some time for the results of experiments to spread even only through Europe. But yes, indeed, the evidence of interference was an important experimental element supporting the wave theory of light. And in this context, also this invisible light could be understood in terms, as we do today, of light waves, or at least waves similar to those which make out visible light, but waves that have a different wavelength, which we cannot see, but still can perceive because it's associated with heat, with energy. This was, at this time, there were already theories of light as a wave, as has already been discussed. However, the final generally accepted theory of light as a wave only emerged after the middle of the 19th century, proposed by James Clerk Maxwell, first in a series of papers in the 1860s, but then in its final form in a treatise published in 1873. And Maxwell's theory was, of course, not only a theory of light, it was a theory of electrical and magnetical phenomena and of how they are connected to each other. For our aims, the important component of this theory was that it assumed the existence of all-pervading electromagnetic field, which mediates electric and magnetic interactions. But in this field, waves could propagate. There was, of course, as already mentioned, the whole question of what is the medium in which this wave propagates, the ether or not the ether. I leave that topic aside. The point here is that Maxwell proposed that there were electromagnetic waves, and of course, this led to the hypothesis that light, visible light, and possibly also this invisible light, should be interpreted as one kind of electromagnetic wave. As is often the case in history of science, at least, For us, it's obvious that this is the right interpretation, but at the time, this was not generally accepted. Especially in general, also the ideas by Maxwell were not accepted for everybody, especially on the continent. In the case of light as a wave, there was the additional difficulty that this electromagnetic field worked well from a theoretical point of view. It allowed to make predictions about phenomena that you could observe, but it was disputed whether or not you should really believe that the electromagnetic field exists out there. This was, of course, also linked to the question of the ether, but not only. And one has to note that the idea of the electromagnetic field was only generally accepted in the 1880s or a bit later, after the experiments by Heinrich Hertz had shown that had delivered empirical evidence for the existence of the electromagnetic field. Hertz, with this apparatus, which I'm not going to discuss now, Hertz showed that one could produce and detect electromagnetic waves, in this case what we today would call microwaves. And not only this, he could also show that you could manipulate electromagnetic waves in the same way in which you can manipulate light. You can reflect them, refract them, concentrate them, and this evidence was was an essential element for the acceptance of the electromagnetic field, of the idea of electromagnetic field and waves in general, and of the identification of visible light as an electromagnetic wave in particular. Of course, later on you would have, with Marconi, radio and more, so the electromagnetic field was even more generally accepted. Now, again, let me just point out something which a posteriori may seem obvious. In the moment in which you start thinking of visible light as an electromagnetic wave, you have this phenomenon of light loses something more of its identity. It's not anymore opposed to darkness, and it's one manifestation of a much broader phenomenon. Electromagnetic waves, electromagnetic radiation, as it was often called at the time, still is called. And from now onward, the study of light will also be part of the study of electromagnetism and electromagnetic radiation. And it is from that direction that the next important development regarding views on the nature of light came. And it came from a discussion which goes still today under the name of the question of black body radiation. Again, this is a rather complex topic which I would like to discuss a little bit more in detail to give you an idea of the historical developments. And to do this, I have to say a couple of sentences about what was the question of black body radiation, what was the question being asked, what answers were being given. First of all, the premises. Yeah, we are at the end of the 19th century. Electromagnetism, Maxwell electromagnetism is well established, and also another branch of physics has become well established, what we call today thermodynamics. The principles of thermodynamics were formulated and generally accepted during the second half of the 19th century. Now, on the basis of electromagnetism and thermodynamics, two opinions became established and are premises on for this debate. First of all, the notion that material bodies are immersed in electromagnetic fields and constantly exchange radiation, exchange waves with the electromagnetic field, so they emit and absorb electromagnetic radiation. I say radiation and waves as synonymous in this context. And of course, this for all wavelengths, not only visible light, but in principle all kind of electromagnetic radiation. Now this is quite easy. The second point regards the properties of what is called still today a perfect black body. A perfect black body is an idealization. Physicists like to work with idealization before they then go on to the real world. A perfect black body is a body which, by definition, absorbs all electromagnetic radiation which falls on it. Although the black body absorbs all external radiation, it still emits radiation. It emits radiation, but it emits radiation which it produces all by itself, let's say, thanks to its internal structure, which of course contains electric charges which are moving. And from the principles of thermodynamics, it could be argued, plausibly argued, that such a body, a perfect black body, emits a radiation, electromagnetic radiation over all possible frequencies, and the distribution in frequencies only depends on the temperature of the body. It does not depend on its size, on its form or anything, only from the temperature. Once one accepted these two premises, then one could ask more specifically what was the shape of this spectrum of black body radiation. So what was the intensity of waves, electromagnetic waves of a given wavelength emitted by a black body at a given temperature T? This was the question. There were, of course, two ways of answering this question. You could try to derive from electromagnetism and thermodynamics with some approximation a formula for black body radiation, or you could try to set up an experiment with some system that was at least a good approximation of a perfect black body and then just measure the radiation. Both these roads were followed around 1900, and of course the expectation was that the two roads would converge perfectly. And this was not always the case. This is one of various diagrams, again from a paper published in 1901, where the different points and crosses are the measurements of the intensity for different values of the wavelengths. And the lines, they represent the predictions of different theoretical formulas that had been proposed at the time. Of course, you cannot really have a formula which is perfectly derived from the principles. You always have to make some approximation, some additional assumptions, so you got different formulas. And what happened was that the formulas which were best, if you want, derived from the principle of electromagnetism and thermodynamics, these formulas did not match experiment, or at least matched experiments only for some wavelengths, but from others not. And the formula which matched best the experimental results was the one proposed by Max Planck. I think this is, his name is well known. So the formula by Max Planck fits experimental results. Now you would think, well, fine, you have a formula which works, case closed. Well, not so fast, because there was, at least in the eyes of authors of the time, and especially of Planck himself, a problem with this formula. Planck, other than other authors who had really tried to derive their formulas from the principles of electromagnetism, Planck had arrived at his own formula by, let's say, trial and error. This is a historically rather complex topic, but simplified, one can say first it was just trial and error, combining pieces of different formulas proposed by other authors. Then, once it was clear that the formula worked, Planck published a series of papers where he tried to show how you could derive that same formula from the principles of electromagnetism and thermodynamics. And he managed it almost with one little problem. He could derive the formula from electromagnetism, but only by assuming that when a body a black body or any body exchanges radiation with the electromagnetic field, that this exchange cannot happen in a continuous way, that there is a minimum of energy that can be either emitted or absorbed by a body for a given wavelength. This minimum of energy was called, according to the use at the time, a quantum. Sometimes people spoke of a quantum of light, sometimes of a quantum of energy, but it was a quantum, a very small but finite quantity. And this, of course, was a problem. Waves are continuous, the quanta are discrete. Should this result be interpreted as showing that everybody had been wrong at the time to think that light is a wave? Maybe it's made out of particles, of quanta. Planck and most other physicists were not of this opinion, also because at the same time, as I've said, electromagnetism had become generally accepted. It worked very, very well for radio waves and electromagnetic cables. And so you could not just go back and say that light or electromagnetism communicates through particles, but how to go on? As I said, Planck and most other authors were not ready to take the quanta seriously, but one later prominent author was, and this was Albert Einstein. Einstein was at the time not yet the prominent figure which he would be later on. This 1905 was the year in which he published the first paper which made him known. And in some of these papers were about the light quantum. What he did was to take this light quantum hypothesis seriously, so assume that at least under some conditions, a ray of light was made out of small discrete packets of energy. He was very careful. He did not speak of particles. Yeah, it's very tricky also from a verbal point of view. Anyway, he used this hypothesis that light is somehow made out of light quanta to explain a series of observations like the photoelectric effect, the specific heats of bodies at very low temperature. I don't go into that. The point is that these were predictions that could be confirmed experimentally or even explained experimental results which had until then been rather mysterious. And so this light quantum started being more and more accepted. One has to say that in this case too, it took some time. It really took some time, and actually this hypothesis of the light quantum was sometimes used against Einstein when he was looking for jobs in the 1910s, saying, oh yes, but that is the guy who takes the light quantum seriously. We should be, yes, the relativity theory is great, but. And it's a fact that it was only in the 1920s that the light quantum, the energy quantum, started being generally accepted, and this was largely because through this hypothesis one could explain what is today known as the Comptron Effect, a phenomenon which can be explained as really the scattering, the collision between an electron and a light quantum considered as a particle. However, as I already said, this in no way was interpreted in the sense that light is made out of particles, because everybody knew that light, electromagnetic radiation behaves like a wave. So what had to be accepted was that light, electromagnetic radiation, displays a dual character. Sometimes it behaves like a wave, sometimes like a particle. This was a big surprise, let's say. It was something that was not really also spoke about very much at this period, but became more and more important because this double dual nature of light in the 1920s became a template for conceiving the deeper nature of all particles. So from there, the so-called wave-particle duality of electrons, protons, and in principle all particles was derived, if not derived, but this was really a template for conceiving of microphysical entities as being neither waves nor particles, but both. This happened in the course of the emergence of quantum mechanics between approximately 1913 and 1927. I certainly cannot go into this detail, but the point is that in this context it became accepted that also electrons, protons, and all microscopic entities which had been thought of as particles display also a wave behavior, in this case too a very important factor in helping the scientific community accept this rather radical view, where was an experimental one, namely the evidence that also electrons, so particles, can be diffracted in an image which we have seen before for light, but this is an image for electrons which display this typical wave phenomenon of diffraction. This is from a paper by not the first one that showed the element, that was by Davidson and Bremer, but had no picture. So to show you a picture, I go to another paper published in 27, and so to make the story short, in the late 1920s, it became generally accepted that microphysical entities have this dual character. Now, you might think that at this point the light quantum stopped being problematic, but this was not really so. The light quantum, which by this time was usually called photon, this was not the case in the beginning, still in the 30s and even in the 40s was regarded as different from other dual entities like electrons or protons. This was because at this time it was clear that photons could be created and destroyed, but it was not clear that this could be the case also for other particles. So the photon was still regarded as something a bit different from other particles, and this only eventually changed with the advent of quantum field theory. And with this, I jump to my last slide, which depicts the situation today, a bit sketchy. What I should say is that around 1948-49, a theory called quantum electrodynamics was formulated, which was a theory that combined Maxwell's electromagnetism with quantum mechanics. And in the context of the interpretation of this, here we are, maybe I should say, going into the metaphysics. This is the quantum electrodynamics, and more in general, quantum field theory is a theory which is mathematical. It works quite well. It allows to predict a lot of phenomena. How exactly you should interpret the different mathematical elements of this theory is a metaphysical question, to some extent still open, but one thing that you can say is that in the context of, say, quantum field theory, quantum electrodynamics, the fundamental structure of microphysics, they are neither particles nor waves, but rather quantum fields, this mathematical object, which are different from classical fields, like the electromagnetic field. You can think of it also as something which you can go and measure. You can't do that to quantum fields. Quantum fields have empirical manifestation also only in the form of protons, electrons, quarks, and photons of these microphysical identities which display wave-particle dualities and are all interpreted as the quanta of the quantum field. So in the sense, this view of the electron as a light quantum has now been largely extended to all microphysical entities, and all of them can be created or destroyed under the right circumstances. And here you see, probably you know the term standard model of elementary particles. This is at present the generally accepted microphysical theory of microphysical phenomena. And all of these boxes correspond to different elementary particles, and the photon, gamma, is now one of them. And at this stage today, you can really say that light, the photon, is exactly on the same footing of as all other microphysical identities. This is, for today, the end of the story, but of course, I put the question mark because being a historian of science, I know perfectly well that usually when you say that's the end of the story, that's not the end of the story. But this is anyway the end of my presentation. Thank you.
Thank you very much. Again, for the brilliant presentation, but also for the brilliant timekeeping. The eagle-eyed observers of the program will have noticed that we have a few minutes more for this particular part of the program than for the other two presentations, which will allow us to, after the initial questions to this paper, to just pick up any remaining questions to the other two presenters. So we will still have enough time to finish for 1:15. So, but let's start with questions relating to this paper. So, open to the audience. There's a question right at the front.
Thank you very much. Could you tell us a little bit more about some of the stuff that you didn't have time to cover in the earlier part, in the part of the 19th century where folks were still investigating what possibly the relationship between light and electrical and magnetic phenomena could be?
So I hope I understood the relationship between light and electromagnetic phenomena.
Yes, could you say a little bit more about, in the early 19th century, how folks came to believe that there was a connection? Of course, this is synthesized in Maxwell's equations, but before that, right.
Well, it's. I mean, I have now to also refer back to the first talk, which also covered that topic quite quickly. Well, first of all, there are two elements. One is a little bit what I said that. Let's say in the first half of the 18th century, there was this transformation where light was not seen anymore as only something visible, but as a manifestation of something wider. The possible connection between light and heat was a topic. And here I must say there was a great variety. If you look around 1800 or the end of the 18th century, there were, for example, in Lavoisier's chemistry, you had light particles and heat particles. And then in other wave theories, you had let's say light waves and heat waves. And there were different versions of all of these views. In the early 19th century, the wave theories of light, especially the one by Fresnel, was developed. And in that theory and other theories connecting to the possible polarization of light provided a mathematical starting point for Maxwell's theory. So Maxwell's theory built upon these theories of light. However, he was mainly focusing on electromagnetic phenomena, on the connection between electric and magnetic phenomena. So it's in this sense, please correct me if I'm wrong, anyway, anyone in the audience, it's an extremely complex story, because for Maxwell and his group, let's say later the so-called Maxwellians, there was, from the beginning, a connection between the light and electromagnetic phenomena, because they connected electromagnetic phenomena to the field and to the ether. And the ether was one part of the wave theory of light. However, for other authors who did not connect electromagnetic phenomena to the ether, this whole part, this connection which was there mathematically in Maxwell's theory was, yes, it was a useful mathematical connection, but it should not be interpreted realistically. And that's why the idea that light is an electromagnetic wave was not was not accepted. I'm not sure this answered your question, because the problem is that one thing is whether a theory existed, another thing is whether it was generally accepted that this theory explained the phenomenon, if you want, at a metaphysical level.
Thank you very much. Over there. Yep. Thank you.
Thank you. Do we understand why the speed of light is so fundamental? Do we understand why the speed of light is so fundamental?
You mean now or historic?
No, not historically. I mean now, currently in general relativity and so on.
Yeah, well, the speed, that light propagates at a constant speed. This was already part of Maxwell's electromagnetism. And actually, it's from there, and on that basis, that there's a special theory of relativity was formulated. So this was, this was, I think, mentioned also in the first talk, that light propagates at a finite velocity was established, was generally accepted in the context of, for example, Maxwell's theory of light. This was also expressed in the mathematical theory. So it's fundamental in the sense that it's an empirical result, and it's also a fundamental element of Maxwell's electromagnetism. And from there also of all the later theories based on that.
Yes, but its unchanging value is what governs the relationships between space-time and mass energy. So do we know at a really fundamental level why that is so? Why it doesn't change?
This will actually be picked up in one of the talks this
is that
afternoon,
later?
which will focus specifically on that. So
sorry
maybe
to
we
jump
can.
ahead.
No, it's fine. But I think we can probably leave that until after that particular presentation. Any other questions? I see one in the front. I just need to make sure that I don't miss any at the back because I'm looking into the projector light. Yes, thank you.
Thank you. That's a lovely talk. I was really fascinated that you chose right at the end to generalize the gauge boson nature of the photon to the other gauge bosons of the standard model. And I wonder if I could just push you a little bit more about why you did that. To what extent in your thinking are the W and Z bosons and gluons, for example, a generalized light? Mm-hmm. Is that why you did it? And if so, or maybe not so, are they historically, in your historical survey, are there early suspicions of generalized light that might have other properties, which actually don't travel at the speed? So those are examples, of course, of vector gauge bosons which do not travel at the speed of light because they possess mass.
Yes, thanks for the question. So first, I should say that I decided to add this view of today also because it was important to arrive to today, but it would not have been possible to do the history arriving to that. So this is why I put it. And then looking from today, I think for me it is, if you think about the nature of light, it's extremely important that that's a place of light in today's microphysics. Yeah, that's it. It's one particle or one quanta among others. Yeah, so I think this is really radical. Yeah, light in a sense has lost its visibility, if you want. So this is one point why I showed that. On your question, well, this is a historical question of great importance, and there is no doubt that for the development of the standard model, so the W, the Z, and so on, for that, at least from a mathematical point of view, electromagnetism or quantum electrodynamics was the template. So the photon as a gauge boson, it was not yet called as a gauge boson, but that structure was the template to formulate the further theories. So very definitely from a mathematical theoretical point of view, that was the line followed. Yeah.
Thank you.
Thank you. There's one question here, and anybody else in the back? Yeah, just over here.
Thank you for a very interesting talk. I wonder if you or one of the other speakers could comment on Isaac Newton's ideas about particles and waves for light. Years ago, when I was young, I read his Optics, and I was clearly he was a particle light man, but he was aware of interference phenomena which he had to account for, and he said that the particles, I think, took fits of being easily reflected or easily transmitted. And he calculated the interval between the fits as, if I remember, it was 1/84,000th of an inch. Now, if you put that into new money, it's about 300 nanometers, which is half the wavelength of sort of visible light. So he'd actually calculated the wavelength of light, as I see it. But I wonder if any of you or any of the other speakers would like to comment on that, please.
Well, on this specific calculation, I cannot comment because I don't know enough about that. Maybe other speakers or someone else can say something. On the particle wave notions that are there in Newton's optics, well, that's from a historical point of view an extremely exciting topic because he has very varied opinions, which also change in the different editions of the Optics. And I think there has been quite a lot of discussion among historians which view he actually adhered to. This is, I think, quite typical of Newton because also in his writings about gravitation, does he really believe that there is a force of gravitation or not? This is a very much discussed topic in the history of science and in the study about Newton. What exactly he means about that it's a mathematical construction and so on. So this is my part of the answer as far as I can go. Maybe.
I don't know, Mark, Olaf, do any of you want to?
I might just comment, not that I have any particular expertise in the details of Newton's corpuscular theory, but as I tried to emphasize in my talk, we don't think of light, say light as a particle, or the ether as a material. All of these people were very aware that if they were particles and materials, they are not like regular matter. They are a different sort of substance. So we can't just say that if he's saying light's a particle, it's like these particles or something. It's a different sort of substance. And so we've got to be quite careful in what we try to take these things too literally by our sense.
You've got the microphone. If you could just, the gentleman over here. Yeah. Yes.
Thanks. This is just an answer to the previous question. I think that Newton's fits were a dim perception of the quantum amplitudes of Feynman path amplitudes. He dimly perceived that that's what you would, something like that. He didn't have the complex numbers, but he dimly perceived that that's how you could get particles to interfere.
Thank you. One more question over there, and then I would suggest. Sorry?
It's really I'll get another comment on the same question.
Okay.
So I'm really just commenting on the same question, but I think, again, God, I'm just commenting on the same question again. I think Newton's view was very much the particles are like mini billiard balls, and that's sort of what we describe when we talk about muons. I used to work with muons and these things. And we contrast that with the sort of traditional wave optics view of light as this sort of big sloshing entity in the electromagnetic field. And we've kind of forgotten that actually this theory, which we've got in front of us at the moment with wave-particle duality, is about somewhere in the middle. So they're not. Newton's corpuscles were like mini billiard balls. Photons aren't billiard balls. They're not really meant to be. They get simplified in these diagrams like that.
Thank you. I think this is now a convenient time to open up the questions to all three speakers. Feel free to stay here rather than disappear back to your seat. If there are any other additional questions or comments on any of the three papers, yes, the gentleman in the middle.
I was actually going to comment. So the second talk, sort of at the start, there was a comment about philosophers don't really see colour as important as things like God or souls. But actually, I mean, I wondered how much that's really true, because in the sense that I'm old enough, as I guess many of us are, to remember black and white television. And I don't think there was any difficulty about watching black and white television or black and white films. So in fact, it seems like from our perception, although colour is a familiar thing in the world, we don't need it. That actually, if you take the colour away and just watch in black and white, it's still perfectly good. So did philosophers, in fact, you know, seriously consider colour, or did they just ignore it, basically?
I'm not sure whether this
was for the second.
a particular.
I can comment on that.
Yes, please do.
Yeah, just television is an adaptation from evolution, because if you're eating a ripe fruit, you want to see it's red, because it's a sign it's ripe. So if you're watching an apple on TV, you don't know if it's ripe or not. Whereas if you're an animal in the wild and you see a red apple, you know you can eat it. So evolution makes us see the information that's essential for survival. That's why you develop things like we heard before. Polarized light doesn't seem to be important for our survival, so we don't see it, whereas color is important. That's why we see it.
That's a different question. I'm saying there are specific things in which colour is important, but it seems like most of the time it really isn't, because if you watch it without colour.
Yeah, but watching TV, your survival doesn't depend on watching TV, whereas trying to find ripe food is. Sorry, that's. Yeah, you don't need it to watch a film, that's correct.
Right. So, could you just pass the microphone to that gentleman? Thank you.
Can you make any comment about what people might call slightly abnormal colour perception? There were, I understand. Hang on. I understand in the eye, for example, there were two red receptors that have they're tuned to slightly different frequencies, and this probably amounts to why some people, let's say, some lady with orange hair will wear a red dress that clashes very badly, and for other people it doesn't look bad.
Well, yeah, sorry, you have to see it in the whole context of evolution. You know, there are defects which are obviously of a disadvantage. If you live in human society, even though you might have a disadvantage when you come to a red light, you still, you know, you go to a shop and you buy food, you survive. Whereas if you're an animal in the wild,
I accept all that.
You know,
it feels like
it's a defect, but we can live with it because
it feels like we are moving into very organically into the lunchtime conversation. So I think this is now a good time to just remind us of the progression of the program for the rest of the day. So we will have, after putting our hands together to say thank you very much to our three speakers once again, we will.
I'm Sam Fletcher. I'm the chair for this afternoon session. The first talk that we have this afternoon is Professor Claudia Maraston, who is from the University of Portsmouth, and she'll be talking to us about elusive light, dualism, and natural limit. Please, Professor Maraston.
Thank you very much. I first would like to thank the organizer, because this is not my usual natural environment, and I've learned so much during the morning session, and I really hope that I can give you something. The other thing that I would like to say, Joanna gave me a title, and that's the title that is printed there. Let's say I made it up a little bit because of the longer time span between your kind invitation and the actual realization. So quantum mechanics entered the way. No, thank you. So yes, I will try to cover the task of covering historically how we got to the speed of light and the implication it has on modern theory for the universe and the microphysics. I am an astrophysicist, and therefore I will also take you into the major implication and connection that exactly this type of theory has on our understanding of the universe. And in fact, I start by showing you the oldest ever emitted light in the universe, which is the cosmic microwave background. It is here shown as a temperature map. The difference in temperature are tiny, of the order of 10 to the minus 4, even less. That's a strong probe of the homogeneity of the universe at that epoch. But before that epoch, there was no light, which is, if you like, another problem we should be discussing. That's the first thing. This was emitted 400,000 years since the Big Bang. So we go back to really the start of things. Before there was no matter and there was no light. So if you like to see big numbers, as astrophysicists are used to, that's the currently accepted value of C. When I give problem to the students, I round this up to 300,000. Do we need all these figures? However, they are actually experimentally verified. So the question is, how did we get there? Also, I wanted to give you the information that I don't know if you wonder why we call it C. C comes from celeritas, which is speed in Latin, something I studied when I was studying in Italy. So we have had several points of discussion in the morning towards the history of whether light should propagate at a finite or infinite speed. The number I just showed you, it's quite close to be a huge thing. And I tell you, the experience in astrophysics is that these numbers, when they become too large, they almost tend to infinity. However, it was everyday experience that light and sound propagates at very different speed. And that's very simple if you think of a thunderstorm, in which you see the light immediately, and you wait a little bit to hear the sound of the thunder. And then according to how close they are, you better find some escape, because it can be bad. Does this mean light travels at infinite speed? It only means it travels faster than sound. So I think this was the question that anciently people started to think about. So one of the first, and I hope the historians in the audience will agree, but please feel free to correct, we find this type of speculation back in ancient Greece, but actually in Sicily, in Agrigento, where Empedocles came from. And he said, he was meditating, and we know this mostly from Aristotle, that the light of the sun must take some time to reach the Earth. We actually know it's about 8 minutes. So its speed must be finite. This is what he concluded. A sort of less than 100 years before Christ later, Aristotle was being quoted for this sentence: light is due to the presence of something, but it is not a movement. For which people have concluded that Aristotle actually was supporting that the speed of light is infinite. So we are already with this dualism, which is not the classical dualism, problem already back centuries, millennia. Hieron of Alexandria added their bit in working in Egypt, in North Egypt, in Anno Domini 62. And he said, well, the speed of light is probably infinite, because when we open the eyes and we look at the stars, this is a beautiful image of the Milky Way, we see stars instantaneously. There is no delay. So you see, you find a way to probe your thinking, and we still proceed this way. The problem is, if something is infinite, are we able to measure it at all? Does it make sense to define a measurement in this sense? So, with a bit maybe of quoting that I'm not reporting, this notion of infinite remained until the early 17th century, with two quotes from two famous researchers, one astronomer and one mathematician, that have been quoted in the morning session. Kepler, to which we do, in fact, we own the Kepler law, for the movement of planets, came to the conclusion that if the speed of light was finite, the Sun, Earth, and Moon should be out of alignment during lunar eclipses. As this didn't seem the case, then the conclusion was that it was not finite. Descartes agreed with Aristotle, and in fact, he went that far, apparently, to postulate that the speed of light is infinite and may even be speed up through certain type of media. The first experiment to try to measure the speed of light, however unsuccessful, is due to Galileo Galilei in 1638, which envisaged an interesting experiment, namely himself and an assistant on two farther away, but not more than 2 miles, hilltops, with a lantern covered by a cloth. And so the experiment consisted in removing the cloth, and the assistant should have immediately ticked something, I don't know what they had at the time, to say, oh, well, okay, that's the time delay, and therefore then you can work out the velocity. The experiment failed for several reasons, but I think mostly the distance was very small. And the reaction time of the assistant is assistant dependent. It's not sort of an objective experiment. And Galileo, in fact, said that he was not aiming to really get, so he was able to find a way out of this failure. But that has changed actually mindset. It was mentioned in the first talk, we actually owe the first measurement of the speed of light to Ole Römer, who was active in Paris and actually an assistant of Cassini. And I want to mention this because there is an interesting story behind, who in 1676 used the moons of Jupiter and especially Io, and the fact that they had different duration, whether the motion of the Earth was approaching or receding from that other planet. And that implied, in fact, different light paths. And so he concluded with this sentence that it did not provide apparently an actual number, but he said this inequality appears to be due to light taking some time to reach us from the satellite. Light seems to take about 10 to 11 minutes to cross a distance equal to the half diameter of the terrestrial orbit. And that's the thing that he published officially. What I wanted to say, Cassini, well known for the Cassini telescope, who was his mentor, actually found mathematically with this measurement this type of oddities before, but he decided not to believe to that. And that's an interesting thing, right? So the student instead decided, okay, instead I think this is telling us something. And the other one was, in a sense, too conservative and decided to leave it go. And now we know how it goes. I found this very interesting. So we can proceed towards modern measurements, and excellent reviews have been given, in fact, before lunch. There are a joint effort from two apparently competitors, Fizeau and Foucault, in 1849. They already used terrestrial laboratories. I wanted to say Ole Römer also is distinctive because he thought that, in fact, the speed of light has to be measured in space, because just space gives you exactly the span in size. Not in time, because we are speaking about the local universe, but in size to make this measurement significant. So they instead, where we are already at the end of the 19th century, mid of the 19th century, they had the facilities to do this in lab. And they found the sea, which is quite very much similar to the actual current value, which to me is very it's impressive. So what do we conclude about this number? Well, C is huge. It's outstanding, right? Think about when you are on your car, if you would like to drive that way. But it is finite, and it has a number that we can work with. I think that's a different thing. Now, these two gentlemen, Michelson and Morley, actually changed history by performing an experiment whose results are not what they were seeking. Working at Case Western University, They wanted actually to detect that substance called ether that has been mentioned before lunch. And so, in the assumption that you can, in fact, detect a motion with respect to these things that you don't see but is there, then the difference in the velocity that they would measure would be detectable. But the experiment failed. It is interesting because being an astrophysicist, I immediately thought about dark matter. And I want to throw this for discussion. Because when we speak about dark matter, which is 30% of the universe, and I will come back to that, we don't know what we are talking about, and we say instead it is not ordinary matter. It's nothing like anything. And it is there. And so this failed in the sense that there was this proved that the ether was existing, or the other way, you say the speed of light doesn't change with respect to the movement that is carried of the source of light. And that will have a catastrophic implication on modern physics. And so obviously then the next step that also was mentioned before, it is a great program that the organizer have written down, because all talks talk to each other. It's very nice. So 1905, the year of special relativity. The speed of light is central. This was a question during the morning session. It is central to Einstein's theory, as I will also show, also to the evolution of stars and actually the light source in the sun. But it comes a bit as a postulate of relativity. Namely, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source. So, crucial, because it is a postulate. It's like when we postulate the Big Bang, the hot Big Bang. Also, the laws of physics are invariant in all inertial frames of reference. That's just for completeness. So C enter in the core of the definition of these theories. And so, again, in the topic that I was asked to cover, I will briefly point out some thought on the relevance of the speed of light to relativity and to quantum mechanics. So, it is completely intrinsic to relativity. It is one of the postulates of our current major theory of space-time. It also implies, for another reason that will be in the next slide, that C is a natural limit. Heavy word to say, both natural and limit, but this is the way we would like. Because the fact that C is constant and C is space over time implies that the time is no longer an absolute. And simultaneity is a relative concept. And that was absolutely catastrophic. When I studied it in my secondary school, I liked that because it was mind-blowing. I mean, in the sense, I'm sure that most of us still don't get it. We accept it, which is a different thing. But it's fantastic. So time is not the absolute. Also, when you approach the speed of light, you have this fantastic twin paradox of time dilating and clock proceeding slower. So astrophysicists verified this with quasars that are emitting supermassive black holes. It's an ordinary thing. Fantastic, but and also, and that's another consequence, if you could travel faster than the speed of light, times start to run backwards. And that's a problem, might be a problem, because this breaks causality. So, in fact, I bet that there are also those who do not like the fact that we have this constant. In physics, we have a lot of constants. And we were discussing over lunch, some of these constants, are they really constant? Are they constant in our universe, in the assumption that there might be others? Or are these constant because we have not yet found a way to actually invalidate their value? So far, they are brilliant constant. So This equation is fundamental, and that's the other connection to relativity. This tells you it's the simplest equation that you can teach the student. The student always remember that. It's brilliant. E equal mass. Energy and mass are the same thing, but a constant. And the constant has that value. But it has to have that value if you want to explain the luminosity of the sun. And that's nearby, and you measure it. So the nuclear reaction, the fact that the sun is now currently converting hydrogen into helium, it does so with this equation and a convenient factor, which gives us the right energy per time. If you change that, you need to change several other things. But especially, that goes back to Empedocles and probably many others. I'm not a philosopher, so I quote just what I know, what I think is safe. That you don't create or destroy, but you transform. And this is fundamental. So I quote just for your leisure, the energy lying within the sun or within a person, order of magnitudes of difference. I will come back to that towards the end of the talk. Speaking about quantum physics, just a brief homage to this fantastic theory, very mysterious, as the speaker before lunch said, that would like to link matter and energy at the most fundamental level. And as it was already said, according in that theory, light and matter both consist of particles which have wave-like properties associated with them. Okay? So we know the entity for light is called photons, and there are many other particles in the standard model, and many more to come. The Higgs boson was just made a few years ago, a few decades maybe. So one thing that we astrophysicists use all the time is the fact that C enter in defining the energy of these photons that we receive from space, with again another super clean, elegant formula, E equal h times frequency, which means times h c over wavelength. H is another constant of nature. I won't talk about that. It's the Planck constant. But there is also this connection in this formula, two fundamental constants, but one is the speed of light. So that's the other relevance. And this is crucial because, and we see this, I will show you a spectra of actual astrophysical object. The energy level are not a continuum, they are continuum in approximation of infinity, but they are actually discretized. And if a pattern of light does not have the right energy to excite atoms, it won't do anything to them. That's all contained in this formula, which depends on two constants, and I acknowledge Niels Bohr and this atom model. So, here I use the term elusive, probably incorrectly in the sense I use it in the real adjective that it means to me, but it seems that there is a theory on elusive light, and I'm not going to that. The uncertainty principle is another thing that I personally liked very much when I was studying, and this tells you that, as we know, it is impossible to fix in the same experiment the position and the momentum. But what is the momentum? Mass time velocity. You have to decide whether you have massless particles. In that case, it's becoming trickier, but in principle, that's the link. So this was shown already. The photoelectric effect in particular really probe the wave and particle dualism of light. And so I can go on. And now let me go into the astrophysics. Who of us didn't dream at some point to travel back on time? I think about this all the time. And in fact, here it's me at 2 years and a few decades later. So maybe this is why I did astrophysics, because astrophysics naturally is a time machine. Because the distances are so huge, when you move into space, you automatically move back on time. And this is the usual cone of the universe, a cylinder in this case, that show you actually the various epochs and the expansion of the universe from inflation the first light emitted that they call afterglow. This is a bit, but it's a cosmic microwave background, something dark in the middle that we still have to understand, and then comes the first stars. The stars are using E equal mc squared to pull out their energy, and they illuminate the darkness, and then you develop galaxy, planets, whatever, and where you see the name of this satellite, we are at the local universe, and I also position in space-time the birth of our sun 4.5 billion years in the past, and our Earth. So anything that has to do with astrophysics has to use C, simply because everything is red-shifted, and time is going backward. So things are extremely connected. We could not do without. So another relevance to astrophysics of C is the realization, really due to Arthur Eddington in 1920, that the energy in the sun must be sourced by something that it was not yet clear in 1920, that is able to convert 5% of the sun. Nowadays we know it's about 10% of the actual mass of the sun, fusing hydrogen into helium, and it was the only type of energy with this equation that would give you the right time scale. So I give you a time scale of evolution of 10 billion years. So in this sense, if we change C, this time is going to change. But we have probes on Earth, on fossils and rocks, that our planet is obviously as old as the sun, or more or less. So this is really important because these are numbers. If you think there is no source of energy in the middle of the sun, if I would be able to switch it off now, the sun would collapse under gravity in 2,000 seconds. Again, if you don't know, if you, again, exclude this E equal mc squared within the sun, and if you think the light of the sun come out of thermal energy, namely it's a heated body is giving away its energy, that all would last 30 million years. So you see the scale of the order of magnitudes of time scale never worked before this equation was written. And now we use it to calculate the complicated things for galaxies up to the dawn of time. So this is the spectrum of light of a galaxy. I have to tell you something that I do all the time. Because it was mentioned earlier when speaking about colors, about the continuum, and then you see. So essentially what these huge assembles of stars do for us, they give us flux on the y-axis, arbitrary units, as a function of wavelengths with no breaks. You have your spectrograph and you collect that. And I just quoted the quantum nature of this spectra implies that the lines are actually uniquely associated to elements transition, which allow us to get the chemical composition of galaxies up to close to the Big Bang, if you're able to get this spectrum. So you see iron, magnesium, all ordinary elements, titanium oxide, sodium, and calcium. You connect this, it's a continuum. I never thought about the colors the way it was described in the morning, so that was interesting. Because for me, all the colors are in this line, and there is no break. But I don't give them name. So this is an observed spectrum, and this is a model spectrum, and I wonder whether this was supposed to be a movie, actually. But I don't seem able to. No. OK. You will have to renounce that it's at my webpage. So these are my theoretical spectra with a resolution even better than the observed one, which are calculated using C, using H as they are, and some plasma physics. But, I mean, the constant are where they are. The number there is a time scale, and this means 3 million years. And that's the emission normalized. And this is how a galaxy evolves. So the movie, if it would have worked, it would have shown you those things, but probably we don't need. That's why, related to this conference, they are called the model of light. So we astrophysicists in jargon, we say, what is the light of that gas? How much is the light of that gas? We speak like this. It is actually the spectral energy distribution. So, and I'm approaching the end, and I will match the time. Of course, black holes, these three colleagues got the Nobel Prize last year, 2020, for having proved that the dynamics in the inner part of the Milky Way is most likely, probably uniquely explained by a hole with mass of 4.5 million of solar masses that provides the distortion that is needed to explain this funny dynamics of central star. You won't see a black hole. So this is interesting because astrophysics rely, as I will show in the last slide, on objects that have no match, no vicinity to light. They are dark. So the gravity here is so strong that it is said in a popular way, but it's right, not even light can escape. But that's because the C has a limit. If that limit would not be there, the physics of black holes would change, most likely. And this is my last slide, and I wanted to throw some food for thought. Arianna, before the lunch, concluded with the same way, and we didn't talk about that, because is this the end of the story? Because the problem for us is that actually 95% of the universe is dark and has no relation to light. We call dark matter and dark energy, and they are vastly disproportionate with respect to the baryons that are just 4.6% of the matter. Because, why do we call it dark? Because they have no relation to light. They don't emit, they don't perturb, they have nothing, they don't have interface. But that's this is a problem we have. And the funding agency keeps supporting these researches, but in fairness, there might be an error behind there, because it's 95%. 5% is the thing we know, the normal matter, the one that interacts in goodwill with photons. And I think I leave you with this slide. Thank you.
Thank you, Professor Marastan. We have about 16 minutes for questions. If you have a question, please raise your hand and wait for the microphone to arrive to you so that folks online can hear the question as well. Over here.
Thank you. Yes, an interesting historical tour, and I was struck when you mentioned Descartes, saying that he agreed, I think with Kepler, that the light travels instantaneously, but I was a bit puzzled by the subsequent comment that he thought that maybe light even sped up, depending on the material. Well, if light travels instantaneously, then there is no variation.
Well,
yes?
That's how, it depends how I agree, it depends how you define infinite, if it is infinite plus infinite, or infinite to the square. Mathematically, you can do a lot of stuff. No, he was a mathematician, I agree with you. That I just quoted
physically.
For completeness, I'm not even sure that we should pay too much weight on that. I completely agree with you. If something is infinite, that's it. That's the actual limit.
Thank you.
Yes.
A question in the front. If you could wait for the microphone, please.
Sorry.
Sorry, just a quick question.
Yep, go ahead.
How were these figures calculated? How did they realize or that?
Yeah, that's a very good question. And in fact, before, when I was preparing the talk, I was thinking, now I need to explain. So dark matter is something that actually came out in the 50s thanks to the work of Vera Rubin that was measuring velocities in spiral galaxies, proceeding from the center of the spiral, which has a circular structure plus the arms, towards the outskirt. Now, the Kepler law, and also the fact that there is little matter there, would say that your velocity will decrease, proceeding towards the outskirts, where the density is lower. And instead, she found, as a surprise at the beginning, but this was a systematic, a flat rotation curve towards the end of the light, well out of the luminous distribution in galaxies. That means that there is something that sustains that velocity, because the velocity comes as an equilibrium between the potential, right, and the forces towards the center, that sustain the velocity but has no direct connection to light. And so I call it dark matter. This study went on systematically, and essentially, in order to explain the value of the velocity, that roughly 30% was found, in about 26%. This very number comes from the Planck satellite, which is a recent mission. And what they do, they fit with a cosmological model with many parameters, including those figures, the profile of the cosmic microwave background. So the first light that I showed at the beginning. You obtain the spectrum of that light with the satellite, is in the microwave, and then you fit the profile with a multi-parameter fit. And the only good fit you find is for these values, especially dark matter. Dark energy was actually probed in '98 through light, and this is very interesting for this audience. What these colleagues in the US, Perlmutter and collaboration, found was that supernovae, which are exploding stars, distant in space-time, would appear fainter than the theory of stellar evolution would predict for those type of stars. But fainter in a way that means that the universe is not only expanding constantly, but it's actually accelerating. So you derive a term that tells you that there is an energy that gave a push to the expansion of the universe, supposed to be at constant speed, in terms of acceleration. This push was measured empirically through the light of the stars. It's like if you have a candle in your hand, and I'm here, and you are there with the candle, and you start to run away and accelerating, and I measure the light of the candle, knowing what it would be intrinsically. That's the probe. Now, but why we call it dark energy? Because to accelerate something, this is normal laws of Newton, you need to provide an energy. Otherwise, the motion is inertial. And so, in '98, so very recently, I did my PhD in '98, this other problem came, that not only there is dark matter, but there is dark energy. And dark energy is 70% of the budget, so it's catastrophically large. So the sum of them, they have both been detected via experiment based on light, so the supernovae or the light of the spirals, but they don't interact with light. So I think they are quite precise. They also give you the age of the universe in this way, which has evolved a little bit since my PhD. Currently, we think it's 13.67 billions of years. And it is a good number out of those parameters.
Great. Other questions? I have a question, actually.
Yes?
So, since the 1980s, the International System of Units has defined the meter as the length that light travels in a second. So since the 1980s, there's a certain sense in which the speed of light has been fixed by the way that we understand our dimensionful units, our units of physical quantities. If that's so, what could it mean to have an alternative theory where the speed of light varies? If by our very system of units, we've set the definition of the speed of light in terms of the distance, that we've defined the quantity that light is supposed to travel over in terms of some fixed number in our system of units, namely a fixed speed of light. Do you have any insight about what it can mean, therefore, to have a variable speed of light?
So I mentioned a bit before, and you point to the right direction. E equal mc square. It completely explains the light received by the sun and its constancy. over 4.5 billion years, together with nuclear physics. But there is a numerical coefficient, which I didn't write down, which depends on the nuclear reaction that you are considering. So for conversion of hydrogen into helium, this is of the order 7 in 10 to the minus 3. So the way out could be to consider the product of this coefficient times C. Then C can vary a little bit, provided you vary the other one, changing maybe the equation of state, such that their product and the mass of the sun remain the same. So there is a bit of space. But not within the theory of general relativity for the space-time and the whole metric of the universe. That's more tricky. So I think the link to the nuclear physics can do it. We are also discussing changes to the gravitational constant G, which is, again, one of the pillars, making a field rather than a constant. I think we can work out a few solutions, but probably not the big one. That would be my opinion, but this may change.
Yeah. Please, go ahead.
Hello, I'm
Hi.
sorry I was a little late, but I enjoyed the bit I got to see.
I didn't notice that, but thanks for saying.
But one of the things, I'm going to throw a hand grenade at you, if that's all right. So we've defined the speed of light as a constant, and let's just assume that well, I'm pretty sure it is. But there's nothing to say that it's the same speed in both directions. Because in order to have information transfer, that's the limit of that is the speed of light. Right, so in order for me to know that you've got my message, you have to send something back. And that whole process is limited by the speed of information, which is the speed of light. So obviously light could change in, say, a medium, but the speed of information is fixed.
But that's the information speed. No,
Yeah.
I agree with you. Yeah, that's
Right,
very insightful and modern.
But what if the universe had a sort of a fast axis, or something that was in one direction? So you can imagine like light was traveling twice the speed in one direction and infinitely fast in the opposite direction, so that the round travel time is still the same. And obviously you have a plurality of different options within that sort of, you have an infinite number of options actually, but we just arbitrarily decide that the speed of light is fixed and it's the same in both directions.
But that, yes, go ahead.
So the question as an astronomer is, I was wondering whether if somebody said to you, like maybe me right now, is there a fast axis in the universe? Could you say, well, we can sort of decide on how old the universe is from our imaging, and actually in all directions it's consistent. Do you know what the error is? Can you put bounds on what the difference in possible speed might be?
Excellent mountains of questions, because this is actually, some things touch really directly onto the research we're doing. So in principle, all our construction of the universe is based on two principles, that the universe is homogeneous and it is isotropic. And therefore, assuming that the light behaves differently in different directions is a problem in general, because it would make cascades into other situations. Images of the universe on the largest scale, and the CMB, the cosmic microwave band, is what I show you, the difference in temperature, meaning in energy, is visible, in fact. You need to measure it with a satellite. Testify that at least up to that epoch it is homogeneous. There comes the light, though, so there is still space to change things. In fact, exactly the other day at my institute, a speaker from Nottingham was arguing that to solve the problem of dark energy, maybe we should give up the hypothesis that the universe is homogeneous and isotropic to solve exactly that problem, so the things could be really. But nobody wants to give it away, because it is at the core of the hot Big Bang, and the hot Big Bang is verified with a few probes. Measure, for example, the helium abundance in the halo of the Milky Way is spot on what is predicted by the hot Big Bang for the rate of expansion that we measure. The other problem we have, the universe is actually flat, so it cannot collapse on itself, which touch upon your way of the light going back and forth. The big crunch should not happen if these measurements are correct. So your speculations are correct, because all of what I'm saying are principles, postulates, right? And there are several in cosmology. So we may give up this and explore other avenues. You're welcome to help. Yes.
Yep. The next question is over here.
taking up the last question about the speed of light not being the same in both directions, was that not answered nearly 150 years ago with the Michelson-Morley experiment? Because, for example, if you drive from London to Birmingham 100 miles, you go at 100 miles an hour there and come back at 50 miles an hour, your average speed isn't 75 miles per hour, it's 66. And so it demonstrates that the speed of light is the same in both directions.
Well, that is not really approaching the speed of light.
This sounds like it'll be a great break discussion. We have just time for one more question, though.
Well, I'm in a dilemma now. I just wanted to comment on that. We know the speed of light is dependent on the permittivity and the permeability of space, and that we can measure. So you don't have to wait for the signal to come back. You can just measure it in one direction, and that's constant. No? You need to know what you can't do that. In order to measure 2 points, you have to send the information back. Wow. So if you had a infinitely slow, you could do it. We'll discuss it later.
This is very interesting, and I don't.
Sorry, can I just ask, you said before that dark energy has got nothing to do with light, but we know as the universe expands, the light is stretching with cosmological redshift.
Yes.
So dark energy is gaining energy, but at the same time, the light is losing energy because frequency is equal to energy. So isn't that light loses energy, dark energy gains energy, so it's equal. That we haven't gained, we haven't lost.
No, but I mean, dark energy seems to kick in, for example, at a certain epoch, which is a coincidence problem, but in itself is not an energetic term, related to light. Okay, there is no interface between dark energy and baryons. There is no interaction. So it is a form of energy, but we think it's not ordinary physics. It is something else. It may be the equation. There is an equation term that gives us a value that is -1. That would be the cosmological constant. Okay, this is one hypothesis, but it's not the only one actually that we have. But it is not really. It was probed through light, but in itself, as a nature, it should not be connected to light.
Okay.
Great. Thanks so much for the lively discussion, everyone. Let's thank Professor Maraston again. I'm very glad to introduce Professor Bill O'Neill from the University of Cambridge, who will be giving a lecture entitled Seeing the Light, Key Inventions that Have Illuminated Our World. Please, Professor O'Neill.
Thank you so much. Thank you so much. So how many years? 2 years? This must be the most important speech in history. It's taken 2 years to write. But you end up still doing your homework on the bus, don't you? Which is what I did. But interesting to try and capture key inventions. And I asked myself the question, why am I here? Why did you ask me? What do I know about metaphysics of optics or color? I mean, I'm a laser physicist by training, and I masquerade as an engineer in Cambridge, applying the practicalities of light, generation of light, and the use of interesting things. And the conversations I've seen in the past few minutes remind me how often physicists argue. Engineers don't argue. It's either right or wrong. It works or it doesn't. But physicists, yeah, what if you did this? And you think, well, yeah, good point. You know, in my lab, it either works or it doesn't, and you just have to get on with it. So, excuse me if I do, and I love physicists, by the way. Mark had a brilliant lecture this morning, which shed light on all sorts of innovations and thoughts. And if we think about the people who have been thinking about light for us, this is just a snapshot of the collection that Mark presented, but all the way back to Plato and the idea of light being shone from our eyes to illuminate the world. And then we see these incredibly important people here. The two of them, I would argue, where James Clerk Maxwell did some seminal work, some work which was beyond human thought, effectively, to bring together electricity and magnetism and create this new vision, a vision that he had himself, largely. And Einstein said he stood on his shoulders in order to develop his own research on relativity. And in fact, Einstein's work on stimulated emission was responsible for the operation of the fundamental operation of the laser. And if we think about Maxwell's relationships, we see these equations which describe the propagation of an electric field, which induces a magnetic field, which induces an electric field, and this time oscillation and therefore propagation of light. I'm sorry you can't see that very well. It's brilliant on my screen. It's not very good on yours. And these equations actually are down to Oliver Heaviside, self-taught mathematician and physicist and electrical engineer who basically developed vector analysis, which enabled 20 of Maxwell's relationships to be converted into 4. And this is what we conceive now as Maxwell's equations, and it was Oliver Heaviside, an unstated genius. I mean, this fellow was phenomenal in terms of his analysis. He developed the coaxial cable. He developed the telegrapher's equations, which explained the reasons why the very first transatlantic cable between Europe and America didn't work, i.e. they didn't know they were propagating electromagnetic waves down a solid cable. They thought they were sending current. And so these equations were established to explain exactly why a multi-billion-dollar investment didn't work. So there are many people behind the Maxwell's relationships, but his conceptual thoughts have created everything that we can apply. And I'm going to change the rules. You spent the morning talking about color. What I want to do is talk about frequency, because engineers want to measure something, and we measure frequencies. And whatever color it is, I don't care. Then when you're a physicist, you talk about wavelength, and you forget about the frequency. But ultimately, the spectrum of light is broad, and it goes very, very, very long, 10 to the 7 hertz for radio, all the way to very, very, very high frequency, 10 to the 27, when we talk about subatomic electromagnetic emissions. And this whole process is divided by engineers into, or maybe physicists if they can agree, on these zones of frequency and therefore application maybe, or scale, or color, or anything else, or energy. So the photon and its energy is the important thing in which we apply as engineers or engineering scientists, because we have both engineering scientists at Oxford and Cambridge and other universities. People who try and apply the science need to understand, what are we going to do with the light? What's its use? How can I generate it? How can I apply it? What can I make from it? And fundamentally, it's all down to this distribution of different characteristics which we can cite and measure and generate and apply. I would argue one of the key inventions was the radio. Electromagnetic transmission of information using electrical systems propagating through the ether, through the air, at the speed of light, at frequencies of 10 to the 3, 10 to the 6 hertz. By the way, it was Hertz that validated Maxwell's relationships. Helmholtz, his supervisor, advised him to do it. Sorry, I've got... See, I drive Macs. They're really good. There we go. Marconi, there were other people working on radio development, but Marconi first developed the commercial concept or the physical concept of the wireless telegraph in the 1890s. And this is on the back of all of the people who invested money joining cities together with wires. The telegraph companies, the telephone companies, who basically said, oh, this is a rubbish idea, there's no way this will ever work. The concept of wireless communications, never. Never trust someone who says never. Lord Kelvin said never, has no future. Of course, you're protecting your investments, so you get the biggest names you can, you sidle up to them, and you say, just tell them it's not going to work. Don't put the money in radio communications, man. And he also said there's nothing to discover, any more to discover in physics just before the explosion of physics in the 19th century. So we have to be very careful about what old professors tell you. It doesn't always have to be the truth. And I have great respect for old professors in this audience who probably thought the same thing. But it led to the boom of communications or transmissions or the connection of people right across the world. Radio communications are the essence of a critical invention based around electromagnetic waves. What's the next one? I would argue television. We just cranked up. I'm going to keep an eye on the frequency. Okay, we're going up in frequency. To carry images, you need higher frequencies. You need to be able to load, modulate frequencies, to be able to pick up and deliver data. And I would argue that television is the next most important invention in terms of the application of light. We're converting images. The BBC, great foundation provider of television and the transmission of information, and if information is power, don't forget. We find that actually there's great competition between Baird's and Marconi's development, effectively established Marconi's 405 line television transmission systems as being the standard that they would adopt. And then we start to convey images with light. Images that shared experiences that immediately allowed to connect the world together, to bring it closer, to bring it more relevant to you wherever you are on the planet. 10 to the 11 frequency, we start to get into microwaves. Just crank up the frequency, man. That's all you have to do. And deliver the power. And what happens is not only are you just changing the frequency, you're changing the way in which this radiation reacts with matter. Because now we're able to not just oscillate electrons in circuits and shake electrons at high frequency to develop more EM radiation, we're able to shake molecules. We're able to vibrate water atoms inside materials to provide energy transfer. We're able to send satellite communication systems and propagate more data, higher data rate, higher frequency, to produce greater effects. We've kind of destroyed the world with microwave comms, don't you think? Everybody walks around Oxford like that. Yeah. Your children sit at the table like that. Your students sit in your lecture theatres like that. So I don't think we've given them the opportunity to see the light. We've given them the opportunity to hide from the light, particularly with the advent of this god-awful technology. Thank you. I'm sponsored by Apple and Nokia. Infrared, well, let's crank up the frequency once again, then suddenly things change. We get heat, we get the sensation of energy. Really, we can feel it, we don't have to see it. Radio waves will pass through your head, your house, and be caught by your aerial, but this stuff, we can feel it. We're now embodied in the presence of infrared radiation. And this is a picture of an infrared camera. I mean, for those of you who's used infrared cameras in the old days, you used to have a liquid nitrogen dewar and a sensitive bolometer that could feel and measure and grade the heat. Now we have these fabulous microbolometers, silicon chip systems which can measure heat, radiation coming from whatever the source is. And this is a picture of my beehives. I've got a little thing that I stick on the back of my iPhone, which I think is a really good thing in this application, and because I can then see where my bees are. I can see through things with infrared radiation. I can gather more information simply because of its frequency change or wavelength change. Your remote control has propagated information via infrared. Heat lamps, the things you shouldn't have on your patio, particularly if it's very cold, because it's not very environmental, are very useful things. You can buy these from Amazon, just by the way. Convey heat. Heat-seeking missiles are very effective when they're pointed at the right particular target. So we can see infrared, much maligned. William Herschel's experiments, and Mark, you mentioned, I think it was Mark talked earlier about who recorded the first or discovered infrared radiation. Herschel's experiment, who was the German-British astronomer who polished his own optics and made his own telescopes and discovered whole galaxies, outbeaten by his sister, of course. Discovered it simply by having a thermometer out, tried to repeat Newton's experiments and had a thermometer and realized that there was measure, temperature, energy had been transferred through white light, through the spectrum, and he was able to pick it up. So, and I guess there are many people who've discovered stuff but not recorded it or had it cited, but infrared radiation is given us lots of activities. What about the visible? Well, we all know this is what we've been talking about all day. Light, visible light, red light, green light, blue light, magenta, or not. Where's Olaf? Or not. How red is red? Man, that's a really red jacket. Yeah, okay, it's red. What we've been targeting to try and allow people to go beyond the space of darkness is artificial light. I could have had 1 million slides on artificial light, but I've kept it down to one. Because we've got candles. Who invented the candle? Well, the first person who were able to produce fire and set light to his beehive. I mean, that's probably one example. The incandescent lamp, who invented that? These people argued all the time as to who was the inventor. This is where engineers really turn science nasty, because they start to patent things. And they have fights, and they have secrets, and they have spies, and they have, I invented, no, you didn't. So you have people thieving from laboratory to laboratory. And this is really because of the importance of providing people with artificial light. Everybody wants more light. Don't want to have to wait for the darkness to go. I was in Sweden last week, and it's now nearly northern Sweden near the Arctic Circle, and it's light all the time. It's great, but it's pretty bloody miserable in the dark in the winter when there is no light. And so this technology is critical to mankind. And we moved on from incandescent light bulbs, boo. They're quite nice light, though. The feel of an incandescent bulb on your skin and your eyes is just calming. The sharpness and intensity of a diode, ugh, my wife hates them, and yet she's supposed to be an environmentalist. And I argue, there's a diode, LED technology is a very critical form of an innovation, and this is an important area. Many Nobel Prizes have been won because of the light-emitting diodes. And we'll see them improve in efficiency. Maxim, by the way, is also claimed to be developing light bulbs. He invented the machine gun, the Maxim machine gun. So he was a pretty broad inventor. Visible light's still part of our world, clearly. It lights us, it shines, it provides life. And the history of the solar cell goes back down to 1839 when Becquerel discovered the photovoltaic effect. And then we have Smith, who basically started to look at electrified lighting and capturing systems. Charles Fritz produced the first solar panel on a roof of a building. That powered the building. And it was really some of the work done by Russell Ohl and creates the first solar cell. And we now see this stuff spreading like a rash over the countryside. Now we get 1 kilowatt per square meter of sunlight on the Earth, in the equator. Okay, up here, a little bit less. But 1 kilowatt per square meter is a lot of power. You think about how much power we're given by the grace of the sun and the nuclear fusion that goes on in space, and this sort of thing is really an critical technology. They're not very efficient, 12, 14%. They should be 90%, 100%, or let's not lose too much. Be like a leaf. Really efficient, and maybe that's some of the technology we have to develop. Another thing that light has helped us with capturing images, capturing data, and the history of photography goes back a long way. When we start to get camera obscure in 1685 and all the way through to silver halide plates and digital technology emanating in the 1990s, and for allowing us to capture images like this gentleman's doing right at the middle of the audience now. What are you going to do with it? Sorry, I don't mean your picture, but I meant all of the images that we capture stay in the silicon chip somewhere and get thrown away when the phone's gone, or get lost in data piles, and we don't have photographs anymore. I think we should ban digital outputs and just go straight back to silver halide films. At least we'll have a history to look after when the world blows up. Critical technology, holography, amplitude, not forget the amplitude of the light, but let's capture the amplitude and the phase. Start to be clever with light, where we've been able to manipulate radiation. And this is the amazing thing. Why question you paying 400, 500 pounds to go and see ABBA who aren't there? Well, you would, wouldn't you? How many physicists are in the room? Would you pay 500 pounds to see a real-life hologram of ABBA? No?
It's not a hologram anyway.
No, it's a projection of multiple systems of projections. But holograms themselves will become a very critical technology position that many, many spin-outs are starting to capture the way in which we can see and convey and interact with 3D information in terms of time, amplitude, and phase, of course. Ultraviolet, well, as we start to increase the frequency, we're increasing the energy of the photon, we're increasing the ability to interact with materials, particularly biomedical materials. So we find ultraviolet radiation applied in all sorts of ways, not just to change the color of your skin, which is a very bad thing, but to look at bacterial identification, fluorescent imaging, fluorochemistry, analysis of a whole host of biomedical technologies, which have really given us the opportunity to to look more closely at the bioworld, not just cure ink and have some white fillings put in your mouth, but that's another really good application. And if we increase the frequency once more, we go to X-rays, and we see some of the technologies that have been developed because of X-rays, having really high frequencies, really high photon energies, which can pass through materials which would otherwise capture electromagnetic radiation. And this is the very first X-ray photograph taken by Röntgen's wife, showing a ring on her finger, and clearly not aware of the health and safety aspects of X-rays, which we've come to learn the hard way as we've used this technology. But it's a critical application in a whole host of industries, not just taking X-rays for medical diagnosis. Electronic inspection, food security, checking what's inside vehicles, understanding the nature of the structure of drugs, of proteins through X-ray diffraction, and a whole host of ways that we've used this incredible, powerful electromagnetic wave to provide information. I'm going to dwell a little bit on the laser because A, that's my field, and lasers are really important across the spectrum. We're not just targeting one particular region. We can look at excimer lasers, neodymium YAG lasers, all the way to the molecular lasers, the CO2 lasers. Why are we interested in this form of electromagnetic radiation or light? Because it's coherent, i.e., it's in phase. All the waves are traveling like one big dance, which is good. It means that I can manipulate the radiation far more easily. It's directional. I can identify and target a color. I can pick off any one of these frequencies that we can oscillate, and I can focus it because it's coherent and it's directional to a very, very, very small spot. So I can produce a very, very, very intense reaction on the thing that I'm trying to change, and I can control the temporal emission of it. An array of amazing people, starting with Einstein, who postulated the principle of stimulated emission, which we'll talk about very briefly, but the fact that there are so many physicists in the room, I'll probably skip those slides. I might dwell on one or two. Basov, this is Nikolai Basov. And what was really interesting is that Townes, an American, and Prokhorov, a Russian, were really good friends at the height of the Cold War and spent time in Cambridge at the Faraday Society talking about microwave amplification of stimulated emission of radiation, talking about really dangerous technology in the middle of the Cold War. Unbelievable. Why? Because people didn't really know what they were doing anyway. And no one had any reason to suggest that they were doing dangerous stuff. The word laser wasn't bandied around cinemas or James Bond movies at that point. It was just stuff they were doing in the 1950s, the freedom to discuss and debate. And that's something I think we're losing, unfortunately. So, laser physics. We talked about the Bohr atom, I think. Claudia, you had a nice shot, better than this, about I want to get my light to interact with matter and promote an energy state from E1 to E2. So we talked about having billiard balls or something like this. Engineers like billiard balls. Forget this probability of oscillation theory, you know. The engineers like to see this thing go, oh, it's been promoted, great. And I've got a spontaneous emission. Nature allows material to emit whatever, whenever, in whichever direction. Einstein postulated that stimulated emission can be forced, and its direction can be controlled. And so if I've got this populated energy level, and I've got this incident photon, which just happens to have the same energy or frequency equivalent to the separation between the two levels, then I can get this photon here to actually stimulate the emission of this energy state. And so I now get one, I get two. Cool. I've got two photons moving down in space. If I maintain this inversion, I can have 4, 8, 16, 32, and within a very short space of time, millions of photons all traveling in the same direction, the same frequency, in phase. That's the power of the laser, and that's why I'd argue it is the most important invention in our history. if you want to know how it works, it's very simple. And to engineer it, we have this inverted material. It could be a gallium arsenide, it could be a gas, it could be a dye liquid, it could be a glass, it could be jam. You can make jam lasers if you really put your mind to it. A jam laser, imagine that. This is the challenge I give to my students, and go and make a laser out of something really cool, which no one will believe, but anyway. What lasers are a story of intensities. Because I like to point to my laser, I stopped working on laser inventions or laser generation because it was the kind of interesting bit, but it wasn't as cool as using the laser and pointing it at something and seeing what happens and how the material changes. And so if we look at the story of laser development right from the 1960s, where Maiman invented the first ruby laser, we've always wanted more power, man, more power, more intensity. And this chase for focused intensity has gone on for decades ever since the invention. And we've got clever tricks like Q switching, mode locking, and this thing happened, chirped pulsed amplification, which got the Nobel Prize in 2018. It's a long time before it was invented and the Nobel Prize was given. And this dramatically improved our ability to produce huge bursts of light in very, very short pulses, because power, energy, pulse length. The shorter the pulse, the more power. The power density is so high that what we really want to do to get more power intensity or density is to reduce the pulse width. And we're now down to 10 to the minus 18 of a second, okay, an attosecond. Olaf, we talked about this at lunchtime. And this is an amazing technology which we use as frequency and dispersion and coherence combined to produce a burst of light so short, it's the shortest thing in the universe, unless Claudia can tell me different. So we're creating artificial light sources in the labs routinely. And it's really transformed the way we as mankind can manipulate light. If we look about excimer lasers, why are they so critical? Well, they're just, I did my PhD on excimer lasers, and they're just really nasty UV lamps. But they're really short wavelength, and they can be really effective in creating silicon chips and using UV lithography to have this big old mask that represents the layer of a silicon chip, flash it with UV light, we image it with a lens, and a lens, by the way, costs about 12 million pounds and is stacked about 2 meters tall and has 30 elements, but gives you a beautiful image on your chip so you can make a circuit layer, imprint it in the pattern of your silicon, and carry on to the next layer. And then produce lots and lots of chips with very high density. I've got the 5-minute warning. We can go even further by having EU lithography, where we're now having 13.5 nanometer radiation to get chips which have node sizes of 5 nanometers. These are the latest chips. These are the ones all the big powerhouse companies like Apple, M chips, M1, M2, are 5 nanometer gates. This is 50 atoms wide. We're using light to manipulate matter at a scale which is approaching the quantum level. The next thing is the diode laser, a very innocuous little laser made of a tiny piece of gallium arsenide, which allows us to send a little bit of light, but couple a diode laser with a fiber optic, and you have the internet. And so over a period of 10 years in the 1990s, this technology was developed in unison to produce the internet. You did not have any idea how that internet was going to change the world. No one did. And yet the technology is delivered routinely with companies at a large scale, and we're able to produce an information age which is just beyond belief. And they're so cheap to make because of the previous technology, the semiconductor wafer production, that they're applied in practically every single part of our world. They convey light, they convey information, and more importantly, they convey energy. We talk about color. What we talk about is energy. How can I harness it, manipulate it, and promote it? The fiber lasers, which are basically, if I take a diode, a doped piece of fiber, like a terbium doping black silica fiber, I can produce a fiber laser. The most efficient laser in the world, with a 100,000 hour lifetime. How many technologies do you know when you sign up and you pay on the dot, they're going to give you a 100,000 hour lifetime guarantee? That's because the stability of these technologies has been driven by the comms industry, who won't put anything in the ground unless you can guarantee it for 25 years. And so we've got a level of technology now which is just huge in terms of its application. It's transformed manufacturing industries. It's cheap, it's robust, it's easy to make, and it's just amazed everybody in the engineering space. We can do all sorts of processes with these lasers. We can do cutting, and every car on the planet is laser welded. Every cardboard box is processed by a laser. Every product you buy is processed in some way by a laser. This laser. Your iPhone has 200 manufacturing operations to make the phone and the box it comes in. And all of the other things has just astonished everybody. And so this quiet, hidden revolution in engineering has gone unnoticed by normal people. All we've done is made you more demanding in terms of consumers. You are insatiable in terms of trying to meet your desire. Your need for change, your need for renewal has been driven by the ease with which things can be manufactured. I'm not sure I think that's a good thing. Well, my children think it's a great thing. I don't have time for this video. It's about 2 minutes. Can I? Okay, so I'm going to put this on my website. Come and take it. But this is an example of some of the fascinating processes that we can develop with lasers in industry, routinely, day in, day out, with robots. Oops. Lasers in defense for an auto given. That's another video. But you can just tap that into the internet. You'll find all sorts of things. But where are we going with our light? Well, with our light, what we're trying to do is to go even more intense. We want to get to petawatt class lasers. I don't want to be mucking about down here in microseconds and nanoseconds, picoseconds. I want to be up here, man, 10 to the 27. I want to change matter. I want to have star-like capabilities with higher lasers. Everyone is chasing this dream. Every continent has a bunch of extreme light sources, which are over 100 gigawatts in terms of power, and they're all over the world. And the race is on to produce the best. And the Chinese are winning at the moment. This is an amazing laser from, it's called the Shanghai Super Intense Ultra Fast Laser. It uses that chirp pulse amplification, which won the Nobel Prize in 2018, by squeezing light and doing things to light that nature doesn't do. That's what I found really cool. You squeeze the light by using clever tricks of optics, classical optics, by the way. What do you do if you've got one of these lasers? Well, actually, there are lots of applications of intense light burst, and it's mainly medical, transmuting radiation, nuclear waste, cleaning nuclear waste. That's a big application that people are chasing now. And nuclear fusion. We make nuclear fusion easier. We don't have to spend 50 years promising. But this is one of my final slides, I think. This is a really, I don't know whether it's a cool idea or a stupid idea, but we had a meeting with this team just before the pandemic about how we could help them engineer this trip to the nearest star using a laser beam that's going to push this sail, and on the center of it is going to be this grain of sand-sized chip with a camera and a communication system and a transmission system that the sail will be pushed for 20 years through the universe, heading towards our nearest star, Alpha Centauri, and it's going to fly by at half the speed of light. And it's going to take a photo, and it's going to send that photo back, and that will test your theory, gentlemen. It's going to send that information back, and if it comes back in 40 years, we have a picture of a planet in the Goldilocks zone with an alien going. It's a 40-year experiment. Let's do it. And they're doing it. This is a real company with real money who are looking for people who will help them. And so it's an astonishing thing that lasers can do. We don't have to wait for information to come from the universe. We can give the universe information. And we can give the universe light it hasn't had before. That's really impressive. And I think, hopefully I've given you a sense of the importance of light, not just its color or other things, but for us as humans, it not just supports life in ourselves, it supports products that we rely upon to have a quality of life. It powers the information and transfers stuff around the world, whether for good or for bad. I'm on the fence, really. But it transforms materials. changes materials, it conditions materials. It does things, it helps us keep safe. Lasers cannot be used to attack people, not allowed in the Geneva Convention. But I can defend myself with them, and that's a multi-billion-dollar business now. They've been around far longer than you think in secret at helping keep people secure. But they're unlocking new science because we're able to probe matter and perhaps the universe and see what is it, how can we test our theories and examples of the world. And this new extreme light sources are creating new tools that we just simply could have dreamt of years ago. And what limits our use of light is your imagination. That's it. Thank you very much. Sorry, I overrun.
Thank you, Professor O'Neill, for that very, shall I say, stimulating talk.
Thank you.
All right. I'm glad one person or two people got that joke. If you have a question, make sure that you raise your hand so that we can get the microphone to you, so that folks online can hear what your question is. The first question over here.
About 25 kilometers down the road from here, there's Culham, where they've been working on nuclear fusion longer than my lifetime, to go back. And they use the tokamak, basically.
Yep.
And this is now all moving over to Toulouse area. I think the project's called ITER or something like that. There is a rival technology using lasers. How's that coming along now compared with the tokamak idea? That's number one question. The other thing is, with these very short pulses, I guess you can measure the topography of the moon quite accurately. I think Galileo just said it was round originally, then put a telescope on it, you could see bumps all very much against what the Pope said should be allowed. So how's that going now?
Well, thank you. That's a very interesting question. There's always been the competition between inertial confinement using magnets and plasmas and inertial confinement using lasers, where you just vaporize a target, the vapor compresses the deuterium, the fuel, and has a burst of radiation. I think the Americans have been leading the way in that sense since the 50s, really, since the thought of lasers, late 50s, early 60s, when masers were considered. It's incredibly energy intensive, and on both cases. The lasers have been promised for 40 years, and they've not done a very good job because they just get bigger and bigger and bigger. But the fact now that we can produce intensity through pulse compression means one could argue that we could look for desktop laser fusion generators rather than labs the size of football fields all stacked together, because you need big chain amplifiers to have longer pulses give higher energy. I think probably tokamak's going to win out in the near term. The laser systems will probably have a good go. There's a new company being set up to look at using short pulse laser evaporation systems with Thales, which is the French engineering company. So the game's not over, basically, but I think tokamaks are winning out at the moment. The distance to the moon? I don't know that much about the metrology aspects of ultra-short pulses. I think we can get decent measurements in place using topographic systems, but I don't know. I don't know the answer. It's changing anyway, isn't it? It's bouncing, it's oscillating. It's bouncing, yeah. This is a relaxation of being caught by the Earth's gravitational pull, apparently. But to ask a physicist, they won't disagree with me. Maybe they will.
Next question in the front.
Thanks. That was absolutely delightful. We'll need to talk about the difference between engineers and physicists and philosophers a bit later. That's going to be fun. But meantime, you say something about the future of medical applications of light. Yeah. I kind of expected that, but you can't do everything. But I think that's really opening up. So phototherapies and so
Phototherapies, photodynamic therapies have been around for 20, 30 years, where selected tumors, for instance, are targeted by a drug which only absorb a particular radiation, and you shine light through your abdomen, for instance, to attack the tumors. Loading gold nanoparticles into tumors which resonate with infrared radiation, produce heating, local heating. There are lots of techniques which can be applied. Laser surgery, of course, has been around since the 60s. In fact, the first laser application was retinal detachment, to reattach retinas using ruby lasers. So lasers and biophotonics, if we want to call it that, is a very strong and growing field. And I'm sorry I didn't capture that in the slides. But yeah, I think we're seeing more and more developmental procedures being controlled by not just high-intensity coherent light, but just light in general. You know, phototherapy, which we thought of as being a thing, is actually a real practicing set of procedures.
Great. And the next question next time.
I was going to ask you about the white photon.
The white photon.
No, sorry,
Olaf.
just a joke.
The white photon. Well,
no, sorry.
Let me just
forget it.
I'm going to finish.
Okay, sorry.
I'm going to finish.
Too late. Okay, the white photon.
The interesting thing about the white photon concept is that in order to get chirp pulse amplification, in order for you to actually, how do you produce a short burst of light? You just have a gate valve and flick it and turn it on and off. Do you have a current which basically pulses to the go button is a very short current pulse? When the shortest current pulse you can get is kind of picoseconds, if you're lucky. So you need to develop optical ways of generating bursts of light, and that's to have a very, very broad amplifier which amplifies so many frequencies in that laser cavity. So many frequencies are amplified, so they have standing waves in the cavity, and at some point they all align to produce a burst, a phase-matching burst of light, and that burst of light is inversely proportional to the spectrum of the amplifier. So one could argue we're generating white light because we're generating every frequency in an ultra-fast amplifier, which just happens to recombine for that moment in space and time to produce the shortest burst of light. The wider the frequency range, the shorter the pulse. And so it's kind of almost there. And Olaf, I think your research is going to produce some really interesting findings. We talked to the single photon producers, the quantum computers. Didn't mention quantum computers. That's for another conference. But that single broad spectrum amplification is where you'd probably find your white photon.
Okay, thank you. I didn't think you wanted to talk about
I didn't, but no, you got me going.
Sorry, can I get back to, you showed the Maxwell's waves going up and down, which we saw more or less on there. Yeah. And I just have a question. We're always told the electric field causes the magnetic field, and the magnetic field stimulates the electric field. But if you got circular polarization, it's actually the opposite.
It just
goes got the electric field.
Circular polarization just has your whole system.
I know, but in that case, the electric field decreases the magnetic field.
Yeah.
So, but from the equations, doesn't it tell us that the one increases the other? So how can you get one to decrease it? Because in a sense, when it's going around in a circle, the electric field goes up and the magnetic field has to decrease.
Well, you have the phase changes, doesn't it?
Yeah.
So, and that's generally driven by the material that sources your polarization.
Okay.
Your polarizer does that, for instance. Mark, where's Mark? Talked about, linear material polarizers. Yeah. You can polarize through reflection. You can polarize through, using Brewster angles. And often the light sources that we use, lasers are very rarely polarized. It's really difficult to polarize a cavity, an axisymmetric cylindrical cavity in anything, because your radiation is in all directions. It's polarized in all directions. It's got unpolarized. To circularly polarized light, what we do is we put it through a mirror, which automatically selects the polarization, retards one axis and accelerates the other, and so you can control polarization that way. Or you pass it through a Brewster window. And Brewster was mentioned in Mark's talk, who did the early work on polarization, and we use Brewster window selection to be able to get horizontal polarizing or vertical polarizing, because we can use the transmissive component rather than the reflective component. But the whole concept of polarizing light for us is really important, because it means we can manipulate the beam once we've created it. We can change its direction. We can select a particular part of it in terms of power or amplitude, and we can make it absorb more in materials. At the end of the day, the lasers that produce have to do something, and we want to maximize that, and we'll do whatever we have to do to the system to be able to maximize it. And polarization is really important. Yeah, thank you.
We have a question in the back. If you could hand it over here, please. No, we need to wait for the microphone because so the folks online can hear. Thank you.
Hi, I asked the question because I'm a local resident.
Okay.
You mentioned the laser, name I've forgotten.
Sorry, could
you mentioned the laser at AWE.
Yes.
AWE is atomic weapons.
Yes.
I live near there. And so are they using lasers in a military application?
Why would an organisation like AWE want a massive laser? It's basically
my question.
If you want to explore the impact that extreme and physical environments have on materials, then what you do is you have a target, you make a target, you stick it in front of the beam, and you whack it with as much power as you can, and you watch what happens. And you can stimulate intense bursts of energy, nuclear explosions, by intense bursts of light. And we've already done experiments where, on the very, very micro scale, with a beam focused to a few tens of microns, half the width of your hair, we can get the same physics replicated that you could from detonating a hydrogen bomb on an atoll. And so energy delivered in a very small point in space and time on a specific material, whatever that material is, can provide you with simulations, real-world kind of replicas of things you can't do in real life. Test nuclear bombs, or test the effects of radiation, physical particles, gamma bursts, all sorts of things we can generate in the lab using these really short burst pulse lasers. The EWE one is the Orion facility is a new laser, and probably about 20 years old in the making. It's about 1/10 of the power of the ones the Americans have in California, but the Americans are so expensive to do tests that the guys in EWE are picking up quite a lot of experiments that could be done on lower cost systems. So you really want to use these energy deliverers to replicate scenarios you can't do in the real world, but you want information about, for instance. Does that answer your question? Yeah, okay, thank you. Exactly, yes, that's the short answer.
Yep.
Yeah.
The next question is over here.
Thank you. Thank you for a fascinating lecture. I was interested, you talked about the Russians and the Americans when they worked together on things. And earlier on, you talked about Marconi and how he invented radio transmitter. But of course, the person who did most of the engineering work was Fleming of the right-hand rule. But Fleming had signed a contract with Marconi that he wasn't allowed to say that he'd done it.
Yeah.
And so Fleming has been forgotten in that, just used for schoolboys or
That's
school
right.
pupils. To
Yeah, but
use
really
his
important rule, right?
Yeah.
Yeah.
So what I'm interested in is this relationship between the academic and the commercial, and then you've been talking about the defense world as well.
Yeah.
And how that interacts, and how does it hinder, does it help? Any views that you might have on those relationships between pure exploration and people making money, or people wanting to spend money on defense?
Absolutely. I have very strong views. I think if you, it's very interesting in the UK, let's say the UK university R&D space, is that if you invent something as a research scientist, you can either publish or you can hold back and license and patent. And the universities are encouraged to do impact and to be measured by their impact, not in terms of number of papers or number of citations or the greatness of the work, but on the economic value of the work that you do. And if you patent, then you lock out the world from that knowledge. And if you patent, you actually restrict the growth of enterprise, because you lock out everybody else from developing comparative systems, for instance, whatever the application might be, for 20 years. I've had patents that I've had in the past that have restricted the growth of commercial technology. I'm not proud of that now, I don't think. Patents are there particularly to make money, ultimately, and to defend your space. I think it would be better, for instance, if we didn't have patents and we allowed free determination of information and publication. Because modern students, particularly some of the ones that I know, who are very keen to have a business, to have a spin-out, to do all the things that Oxford and Cambridge and other universities are great and good at,
is the entrepreneurial side of life actually kind of puts blinkers on us and restricts knowledge transfer and sharing. It's always been like that. Edison, Swan, and beyond. Patents are not a new thing. They've been around forever. They just leave a bit of a bad taste in your mouth, that's all.
We've got about 8 minutes now where we have where we can ask questions either of Professor O'Neill or Professor Maraston. So if any of you had questions for Professor Maraston and you weren't able to ask them, we also have an opportunity to do that now as well. Please, right here.
So I was going to ask a banal colour-related question. So white LEDs, I assume, are not actually white in terms of what they're actually emitting. What frequencies do they emit, and do they vary?
White LEDs, well, they can either be generated by having infrared LEDs hitting a phosphorus emitter, so you get a phosphorescence or a fluorescence, or they can be tuned RGB emitters, which are collected together under a glass bulb. It looks white. Is it the colour, or is it your perception of colour? That goes back to the morning session, really. What's colour? I don't really care, I just want the frequency. I can measure frequency and its intensity and its relevance. But white LEDs are really coming on in leaps and bounds, actually.
Yeah, I was recently at a concert where they had white LED spotlights, they're really intense lights.
There is also the thing called the continuum laser, which is a laser which produces emission at all wavelengths, so it looks white. It's not a white photon, because there are lots of multicolored photons being generated, and the continuum output is a white source. It's very, very intense, and it's used for biomedical applications largely. And you can select the particular frequency you want from it. White light, yeah.
A question from Professor Maraston.
You mentioned that there is a plan to travel to the closest star, to Proxima Centauri, I presume. So why would you like to go there?
Why would I like to go there? It's not me.
Not you, but in the sense that the ideal target would be...
Because there's a planet there in the Goldilocks
in
zone.
the Goldilocks, okay.
So it's looking for extraterrestrial life.
That's it, okay.
On a tiny little chip with a material they haven't even got a clue what. It's got to be so light it doesn't drag this little grain of sand down. It's got to be deployable. It's got to be sufficiently technological that it can withstand gigawatts of light shining at it from the ground with an array of lasers, not just one laser, all targeted like a ground station where all the discs come up. It's got to be deployed in the outer regions of the atmosphere, 200 or 300 kilometers, where it's not going to be dragged by the atmosphere, and then deployed and then fired. And then it's got to spend 40 years or 20 years going out there and then 20 years sending the information back to the same ground station, apparently. So this has been thought out. This is not madness.
No.
Why? I don't know.
No, for the
I
extra,
don't have
for the
$100
planet
million
is good.
to waste on even thinking about it. And it's costing $100 million to think about it.
Good. And related to this, there are plans to build a radio telescope on the moon. It would solve a huge amount of problems that we have on Earth, and it could be sizable, unlike the Hubble Space Telescope or the James Webb. Could your technologies, that type of technology you describe, be involved in these plans?
Into making stuff on the moon?
Yes.
Well, I guess lasers have been employed, solar-powered lasers have been employed up in space to do things. There's plenty of light in space, actually, so if you can use your silicon cells to convert light into electrical power, you can drive lasers pretty much anywhere. The moon's a really good material for 3D printers. So you can get a kind of pseudo-metallic material from moon dust, and NASA's already done experiments on building stuff with lasers on Earth for applications on the moon where it's abundant, the material. But companies like SpaceX are planning on launching, allegedly, 2 rockets a day by 2025 that can carry 100 people each. So the population of these bases is the likelihood is going to increase quickly. And you might get your wish to go into the universe that you spent so long looking up at, where you can be in it.
in the green shirt.
Sorry, just a very quick question. You did show numbers in some of the slides for the efficiency of various lasers with time.
Yeah.
So just out of interest, the Project Starshot firing a sensor at Alpha Centauri.
Yeah.
If you want gigawatts of big laser, what's the upfront energy cost for the rest of us?
Yeah. Well, you're going to have to build a couple of power stations next door to it. We're going to have to collect the power from the whole of America probably and tap it into this particular footprint. Gigawatts of power, 100 gigawatts is the argument. How many megawatt power stations is that? A lot. So power is the big problem. And again, there are many problems which are not necessarily insurmountable, but they're certainly, for a brief moment in time, you might take all of the power of, half of America's electrically emitted power for a second a day, pulsing it, keeping it moving, using photon pressure to push the sail. But you're right. See, ne'er-do-wells like you just kill ideas completely. You should, where can I get the power? Not how am I going to get the power? But no, it's a very good question.
Would it not be more efficient to put that in?
Could you use the microphone, please?
Would it not be more efficient to put that in orbit, the laser that pushes it to Alpha Centauri?
Yeah, if you had big enough solar panels to collect the light to be able to fire and produce the beam. I mean, we've got lots of electricity in space.
I just mean to get rid of the atmosphere.
Yes, there is definitely a problem of atmospheric propagation, yeah.
Great.
I mean, what we're starting to see now is visible comms. We talked about communication from radio, microwave, etc. A lot of the interest in space now is laser-based comms, cranking up the frequency even more, because microwave radiation, the frequencies means data rates are very low. What you want is optical frequencies and optical communications, which require line of sight and atmospheric disturbances to be massively minimized or eliminated. I think, if you get to the point where you can produce solar collectors on the moon, then you've got a much greater chance of having these systems.
Is this Alpha Centauri laser?
That's basically an terbium laser, so it's running at sort of 1 micron wavelengths. So
Which color is that?
Sorry?
Infrared. Okay.
Yeah, it's infrared, so it's in that sort of frequency range, and it's just under 1 micron, and it's 65% efficient, which is pretty efficient. The first laser was 0.01% efficient. So it's 4 times more efficient than solar panels. So it's not the rate limiting technology.
Let's thank Professor Neil again.
Thank you very much. It was a pleasure. Thank you.
For the summary of the day's proceedings, we have Professor Tom McLeish. Please, Professor McLeish.
Great. Well, Sam, thanks very much. And thanks, Joan. Thanks for inviting me here. I have the impression that those of us who are speaking, maybe those in the audience today, are a club of people who aren't quite sure why we're here, but we're learning during the day why we're here. And my son's a jazz trombonist. Our son's a jazz, and so he's taught me everything about jazz that I know, and I'm realizing that this is a kind of riff, a jazz riff on the theme, because I didn't know what I was going to say this evening right now until I heard what all the other speakers and all the great questions during the day were going to say. So I don't know whether it's a nice tune or not. We'll find out. But I've really enjoyed the day, and I just wanted to say thank you before I said anything else to all the speakers who've done a tremendous job, really interesting stuff, and to all the organisers too, very much. So here goes. Well, as promised, so I've got a few themes. I think I've 5 or maybe 6 themes. Quick, and we'll get some 10 minutes at the end. One is, we've learned a lot of this is, of course, history and philosophy of physics and engineering, I think. Isn't we've had. So the philosophy of engineering we've had from our resident engineer, but the point of the history of all these things is long. Now, of course, Mark, knew very well that Snell did not invent Snell's law. In fact, wasn't it Feynman who said that the name one attaches to any scientific law is not the first person who's thought about it, but the last person who thought about it before it sort of got fossilized. But anyway, so Ibn Zal, this manuscript only turned up to Western eyes in about 1993 or 1996. I think it's Ibn Zal's first millennium treatise on burning instruments, and that's Snell's law in geometric form. It's the law of signs. There's the instant and refractive ray up there, and Ibn Zal then uses this as an engineer to make burning glasses that focus light perfectly. So it really brings all our themes together. But there's a name which hasn't been mentioned today, but I'm going to mention her name today because it's an Oxford and a British name, and it's probably the greatest natural philosopher you've never heard of, if you've never heard of him, but I'm sure all of you have, which is Robert Grosseteste. Robert Grosseteste is fascinating. He was the first liberal arts tutor to the Oxford Franciscans, right here where we are now, in the 1220s. And round about that time, he wrote quite extraordinary mathematical treatises on natural philosophy, on physics subjects, on sounds, on the sphere, on comets, impression of elements, and to our purpose today, wrote on colour and on rainbows. And so there's a project going on between Durham and York, where I come from, and Oxford, based at Pembroke College here, called the Order Universe Project, where we gather around astrophysicists and engineers, and Latinists and historians and philosophers to read, translate and edit and comment on, from a scientific point of view, Grosseteste's manuscripts. So this is just to add a little bit of detail to what Mark actually knew about, but he cut those slides out, which I'm sure we're grateful for, but I'll put them back in. I was going to do, there we go. As an extraordinary conjecture Grosseteste makes in his treatise on the rainbow, which I've quoted, he gives colour three quantities: purity and impurity, clarity and obscurity, and greatness and smallness. So in his De Colore, he mathematically, in about 1220, describes a three-dimensional abstract colour space for colour. There's absolutely no question about that. That's not conjecture, because he does all the combinatorics. What he then does is agree. Now, for tea time, I've understood Mark's colleague. A single rainbow does not cover the colours, the gamut of all colours. But Grosseteste makes the claim that if one considers all the set of all possible rainbows, which is a rather elegant and rather, physicist abstraction, almost mathematical abstraction, consider the set of all possible rainbows with, of course, all colours in all rainbows. Rainbows in different types of cloud, and rainbows illuminated by different colours of sunlight, redder light at the sunset. And for example, we have a 3-parameter angle, droplet type of cloud, and sun altitude, which can parameterize colour generated by rainbows. So this project did precisely this. Now, we didn't do what Mark's colleagues done to measure the rainbows photometrically. We calculated them. Through atmospheric absorption, geometric optics, physical optics, and everything. This work was led by Hannah Smithson, who's a professor in experimental psychology here, and at Oxford, I thought, and at Pembroke. And I thought you'd just, in case you didn't believe me that you get different rainbows from different types of cloud, you can generate this in your college backyard. Look, here's a generated rainbow with large drops near the spray at the top and fine spray at the bottom. And can you see that the larger drops give you more saturated colours and the smaller drops give you less, because of diffraction, you see? So that immediately brings you in and out of the polar coordinate colour circle. This is what Grosseteste is talking about. And here's a beautiful, now each rainbow, here's a section through the colour diagram, in slightly different coordinates. The A and B coordinates is what the experimental psychologists use. A single rainbow is that spiral. And rainbows with different droplet sizes give one this net of different spirals, and in a full three-dimensional color space, the whole thing looks like this. That's a two-dimensional complex surface. Oh, the spiral is because of the supernumerary bows. And you can see, I imagine, that when the sun sets and the whole thing gets redder, that net is dragged through, not quite orthogonal to its surface, but not parallel to its surface. So it is indeed the case that the set of all possible rainbows maps out a big chunk of visible colours. There's a colour space. There's a paper of this in the Journal of the Optical Society of America, and the editor was absolutely delighted that reference 1 was our Gross test de Iridae 1224, although had a little bit of difficulty finding it on the internet. But that's an Oxford-flavoured thing. History is long here. Okay, history is long. Rainbow history is long, and I didn't think we should leave the rainbow without tipping our hat to, I think, the most extraordinary example of serendipitous double discovery. Namely, in about 1306 to 1308, both Kamal al-Din al-Farisi in Baghdad and Theodoric of Freiburg, who's a Benedictine monk, both had been reading, though it's not quite, the reason they did it at the same time is because they'd both been reading Al-Haytham, Ibn Al-Haytham. Well, of course, Al-Din had much before. Al-Haytham's great work, Optics, had just been translated into Latin towards the end of the 13th century. So the idea of building a camera obscura, getting your glass-blowing mates to blow you a sphere of glass modelling a rainbow, a raindrop, filling it with water, with a little bit of dust, and then doing the Newton thing that Newton would do for that famous prism experiment 350 years later, but in the more relevant to the rainbow setup of a spherical rainbow model in the first decade of the 14th century. That's what they both did. And here's Theodoric's diagram of the double reflection. That even also states he noticed double internal reflection, which would produce a second rainbow, fainter than the first, outside it, and with its colors reversed. Oh, wait. And isn't it lovely when a theory of physics not only explains what you were looking for, but gives you something else you weren't looking for? Echoes of Dirac there. Interesting, worth saying that the deeply entangled history of theology and science, particularly around light, hovers around all discussions of light, obviously. I mean, we should also tip our hat to that. Theodoric is explicit about this and names his inspiration for studying light as the extraordinary natural philosophical poem in the Book of Job, which I don't know if you've ever read it. It is not a religious campaign or anything. I'm just saying if you haven't read the nature poem in Job chapters 38 to 42, please don't let the sunset go down on you today before you have. It's an extraordinary Semitic, ancient Semitic essay on the importance of natural questions. There we go. Colour, objective or subjective? Well, so there are lots of examples of why colours lives in 3 dimensions. We've seen in a beautiful resonance, these 3s come everywhere. I've introduced the rainbow 3, which was implicit in comments by both Mark and Olaf, but there we are, the 3 cones in the retina. We've seen this, the red-green colour cube. There it is again. Here's Gross test's color cube. But I just wanted us to make sure we all understood that color is not a function of frequency distribution or wavelength distribution. So Goethe is right about color being perceptual. Of course, Newton is also right, and Young is also right about being the physical generators of color being out in the world. I've got to the point at which I think actually those early theories of vision, the weird extramissive ones, aren't entirely mistaken. Because now we know about Bayesian inference. If you think about perception as the entire perceptual chain, not just the eye, but the cortex is emitting visual priors all the time. And it's Aristotle, actually, who talks about the meeting of incoming rays and outgoing perceptual rays that I think gets closer to the entire psychophysical theory of perception. So which is the most pink? of those two folders, I mean, this could be, it's the same. It's the same color. Famously, you know, A and B have the same intensity. So your whole perception can be tricked all the time into thinking that things are unequal when they're actually equal. Keep your eyes fixed on the little cross in the middle. Keep them fixed. Don't move. Fix your gaze on that little black cross. Keep it there. Keep it there. Now what do you see? For whom have the little pink flashing things disappeared to be replaced by a green one going round and round? Okay. Now go back and check to see whether there's a green thing going round and round. No, it's not. Okay. There's nothing green. Oh, except if you think of green as negative magenta, then it's there. So sure, we can see negative colors, and here it is. But whether we see negative colors or positive colors depends on what we're adapting to and what our environment is, and depends how long you or she or he or I have been looking at this very famous color constancy figure. So let's remember how subtle color is. Yeah, isn't that gorgeous? I love it. There's been a wonderful light that music has hovered behind our day, as has a certain Anglo-German flavor. And here we move on to Ariana, who reminded us, and a particular Anglo-German family have been with us at least 3 points during the day, namely Wilhelm and Carolina Herschel, from part of the Hanoverian dynasty, which is why, you know, our royal family is still mostly German. You know, they only changed, it's only the name that isn't. And so there is, of course, this long Anglo-German history in both music and history and indeed royal politics. There they are. You know, it's worth saying, Herschel himself, did you know Herschel wrote 25 symphonies? 3 oboe concerti, many oratorio. That's his manuscript of his, goodness knows, and what, 12th symphony, I think, perhaps his 13th symphony. But it's also was the first astronomer to realize that aperture is everything. And yes, size matters. It's not the length, it's the width. Telescopes, folks. That's his famous 40-foot, actually it's like a 3-foot mirror. This was almost too big to be serviceable, though it did discover 6 satellites of Uranus. Behind all this music and physics dance has been, of course, the mention of waves. The quantum theory of light is the excitation, Claudia reminded us, the excitation of quantum fields, the vibrational oscillating excitation of vibrating fields. And this could be a violin string, or this could be 1 photon, 2 photons, 3, 4, 5, 6. It's a harmonic oscillator. I've been trying to think actually about how the musical aspects of William and Caroline, who she was a wonderful musician as well. She was a tremendous soprano performer, and then of course a discoverer of 8 comets, an extraordinary astronomer in her own right. How that musical substratum of their minds fed the creativity of their scientific minds. It's an open question, but I'd be really interested to hear your practical scientific philosophical talks on thoughts on how these interdisciplinary creative energies work at the level of real genius, which is what we're seeing here. I'm just fascinated by this. And no physics PhD course, apart from one that Mark and I are working on to our knowledge, actually includes as a graduate school course a theme on how to be more creative as scientists and more imaginative than you would be if you just stuck your nose to the grindstone all the time. Anyway, there we go. There's another theme of here we're getting a bit more philosophical, or maybe theo-philosophical. There's been this lovely theme of light and darkness, introduced by Olaf, you know, negative light, but picked up again by Claudia, whereas the whole dark matter. And so we've been playing with light and darkness, and there's resonance here. And I think we should be more. I think actually, HAP, we've had lots of history. We've had lots of physics. We've had quite a bit of engineering. I'm not sure we've had quite as much philosophy today as I was expecting. So let's chuck a bit in, or the history of philosophy, the history of the tension between light and dark, both actual physical light and dark and metaphorical light and dark, and theological light and dark. It was C.S. Lewis in his wonderful book, The Discarded Image, of the medieval cosmos, which I think presaged the work I later did with my medievalist friends on Grosseteste in a wonderful way, who pointed out that for the medievals, outer space was full of light. It was the realm of light, as Milton in Paradise Lost talked about the flight of Satan through the chaos of outer darkness and into our own cosmos. He calls them the happy climes that lie where day never shuts his eye, up in the broad fields of the sky. Space wasn't black, space was full of light. And so there's a historian of science, Vladimir Brilak at Durham, who's going around giving seminars on when space became dark. Of course, I'm trying to tell him that the sky being dark is about direction of rays. So you can have space full of light, as astronauts know only too well, at the same time as the sky being dark. And we've seen, so there's that, which is also a theme that's been running through our day, the polarization of the sky, the two-dimensionalness of the sky, and the three-dimensionalness of space must not be confused. But what the tension between light and darkness makes me think of is this great benefit of what the theologians call apophatic thinking, and how physicists in the last century have increasingly found this useful. It's when interpreting quantum mechanics, it is you're on far safer ground to multiply explain and articulate what an electron is not, than to try to say what it is. Claudia was wrestling with this, weren't you? Is it a wave or a particle? No, it's neither. It's a quantum thing and behaves mathematically in this way. But we're caught between a desire to be realists and an increasing burden that it's the path of idealism that is the one that one has to tread for the moment. And this idea of true illumination coming through darkness is a very old one and goes back to one of my favorite patristic thinkers. So Gregory of Nyssa is the most scientific of the patristic fathers. He's quite extraordinary. There's a wonderful treatise he has called On the Soul and the Resurrection, which sounds like a bit of crazy Christian theology, but its core is all about doing experiments of things you cannot see. Like the air in a bottle that one detects scientifically because of the water fighting its way in, and the fact that we know the moon is a sphere, not the projected circle. And he's arguing about the ability of the human mind to recreate a three-dimensional universe containing invisible substances. But as he gets more and more mystical, he becomes more and more fascinated by the way to truth being through darkness, which by which he doesn't mean evil, he means understood ignorance. So he says, what's it mean that Moses entered darkness and then saw God in it? What's now recounted seems somehow to be contradictory to the first theophany. In other words, if Moses saw light, now he sees darkness, how can he know more? Surely he knows less. For then the divine was held in light, but now he's seen in darkness. And what Gregory then goes on to say is that greater truth is eventually understood in this darkness. He calls it luminous darkness. What happens, I wonder, when we all start to think apophatically is the term about this? And then finally, of course, we get to Bill and the future of light. And I wondered about where we think what the future of our philosophical thinking about light might be. As our technology and science of light changes, so the meaning of the metaphor changes. I'm fascinated, for example, by the metaphor that runs through the ages of what we do as scientists. Or as natural philosophers, as we used to be called. One of the great metaphors for doing science is, quote, reading the book of nature. It goes right back to Augustine, to Cicero.
There's medievalists who talk about it. Galileo famously talked about the book of nature being written in mathematical language, and hieroglyphs. Robert Boyle talks about it. But the problem with all that, as in all metaphors, is that when the technology changes, the metaphor shifts too. A book is a very different thing to Cicero when it's a scroll that you have to read through, and everyone doesn't have a copy of the scroll, or to the early church invention of the codex, which is an extraordinary random access technology, the best technology of information access, the best leap, hugest leap ever happened is from the scroll to the codex. But to ebooks, whatever, what's it? Maxwell said, commented on this metaphor of the book. He said, no, it's not like a book, it's like a magazine, because you can jump into any issue. Well, okay, so there's a problem with the book of nature metaphor. What becomes to the metaphor of light and darkness, or being good and evil, or truth and ignorance, or what we know and what we don't know? As light becomes more manipulable, more entangled, we could have said, as I think Bill mentioned, or someone mentioned, a little bit more about the vehicle of photon entanglement as the future of secure communications, but also fast communications, quantum computing with, when light becomes not just that with which we illuminate the world, but that with which we compute and think about the world. Whoa, something might happen very differently with light. And one day we get to go to Alpha Centauri, apparently. That's Alpha Centauri. Thank you very much for the day, folks. That's it. Bye.
We've got about 5 or 6 minutes for questions. In the center, please.
Just wait for the microphone so the people online can hear you.
Thank you very much. Just to add another aspect to light, it's so-called the uncreated light. I just opened a discussion on this because you mentioned Gregory of Nyssa, and Gregory of Palamas in the 11th century speaks about uncreated light. He's not the only one, but he is the most known, which comes from inside. And I think everyone knows what I'm talking about when I say the light come from inside people and is reflected on their faces, but also if I look at what is now on the screen, we can see the light comes also from inside the universe.
Yeah.
Palamas is an important name in this discussion, and also I expected more philosophy today.
Yeah,
okay,
no, thank you very much. Yeah. So and I think that, I'll just say one little thing that resonates with what I was saying. So the inward uncreated production of light, both its theological and anthropological resonance, we're increasingly understanding what that means as we understand cognitive psychology. And I think the outward radiance of priors of the world that meet the incoming world, and so uncreated light meeting created light, if you like, reminding us that even perception itself is a creative act, which, by the way, Sam Taylor Coleridge knew all about that. But yeah, it makes me think of poetry. Yeah. Cool.
By the way, I was asked from the history faculty, but I never feel that philosophy. I took philosophy, so I know something about this.
Great. Good.
Next question with the Olaf, please.
Make up your minds, gentlemen. Yeah.
Professor Muller made my day by resisting metaphysics. But
I ruined it.
You questioned it, and you brought so much metaphysics. And you basically said science is ontological. But we heard today that its resolution, although they didn't say in this word, the resolution of science is evolving. I wonder how you could resist in front of this evolving resolution and bring so much metaphysical aspects to our modern evolving science?
Because I think the way we think about the world is four-dimensional space-time, if you like. Rather, I don't think we forget the past. I think the past, I don't think we fossilize the past, but I think it is important to recognize that the past informs our thinking, whether we are explicit about it or not. So the value that I would add to doing philosophy, I mean, the trouble with metaphysics is, as Olaf pointed out so well, metaphysics just means the book after Aristotle's physics. What else you want to make it mean is up to you. But if you ask me why do this metaphysics stuff and why read ancient authors when we've all got, you know, we're all looking towards the future and we know what we know now, and they didn't know as much as we do. Well, for a start, I'm not quite sure that they didn't know as much as we do. They thought about things in different ways. But the point is this, that our concepts, our language, our metaphors are inherited from all this stuff. And I think it is better, I also think it's more interesting, I suggest it's more healthy to know how our thinking is going, to know what narratives affect our thinking. And to know which giants on whose shoulders we stand, sometimes forgetting we're standing on their shoulders because we're looking at the horizon. So I'm prepared to defend this. And by the way, you get to do new science. So the Gross Test project, by the way, so here's a practical cashing out of what I said. When we began this about 12 years ago, when we as physicists started to work with the medieval scholars, because it looked like a bit of fun, right? And it was clear that these lovely historians of science could translate medieval Latin like there's no tomorrow. I mean, and the paleography of these hieroglyphs, we couldn't even work out whether it was a letter A or letter E. They could read this stuff right off. But the mathematics you need to understand what Grosseteste is saying about the cosmos or about color, as stuff that we had. I mean, they were only good as Latin in today's educational system because they'd given up the maths when they were 13 years old. So you have to read this together. Now, what we hoped we'd be able to do is to generate, therefore, more accurate translations, editions, and more rounded commentaries of this work. What we didn't expect, and it's happened with every treatise, at some point someone says, like that conjecture, that Grosseteste says all colours are spanned by the set of all possible rainbows. Well, did anyone ever check that? No. Could we do it? Yes, we could. Let's do the calculations. That's happened not once now, but 10 times. So there's a whole slew of papers in Nature Physics, Journal of the Acoustic Society of America, I mean, serious journals, scientific journals, with new science that's actually a bit edgy and imaginative, that was inspired by helping our humanities colleagues to understand ancient sources. So I do it for the Nature papers, me, but yeah.
Great. Could you make it quick? All right, please.
Sorry, and I'll be quicker.
Thank you very much for this fascinating presentation. I wanted to connect to this fascinating stuff about the spiral representation of the colors of the rainbows. This is, I understand, simulated.
Yes, that's right. Okay. It's all that's simulated, yeah.
I wanted to share with you a startling experience which I had when we started trying to simulate the colors of the spectrum.
Yeah.
And what we did is we really run a good computer simulation of what gets through the prism and so on when it comes from the sun. And then it was calculated into our color space and we compared it with the actual things that we saw. And this didn't match. I was quite shocked. It didn't match, particularly with the yellow. So the yellow which was predicted by the machine looked much more yellow than what you see in actual experimentation. Right. And I'm very worried about it because I have the feeling there must be something wrong in the model, probably not in physics, but more in our representation of color space. Right. But the yellow is a problem there. And I wanted to say that nice as though this representation is, it should be checked with the actual data and there should be the measurements made.
Well, thanks to today, that's what Mark and I are going to do, because Mark, we're going to get in touch with Lee, no, your colleague who measures that. I didn't know that anyone photometrically measured rainbows, so we're going to check all this. Fantastic.
I'm afraid we're out of time for today, but there will be time to maybe have a chat a little bit afterwards.
And
Let's thank Professor McLeish very much.